So David, shall we?
Sure.
7 o'clock, we're over 100 and we're recording.
Right.
Okay, so good morning, good evening, good afternoon, wherever you are. Thank you for attending this first day of the 2022 IEEE CAS Seasonal School on AI ML for IC Design and EDA. I'm Andrew Kang from UC San Diego. David Pan from University of Texas at Austin is the co-organizer of this seasonal school, and it is co-sponsored in some sense by the Telos AI Institute. So we're very pleased to have so many people attending, and we have a great first day lined up. This is our overall agenda. We'll be meeting at this time on 4 days, Friday and Saturday of this week, and Friday and Saturday 2 weeks from now. And you all have the Eventbrite registration and the agenda. So it's a very exciting and very broad coverage of AI and ML applications to modern design and EDA. Today, the session focuses on deep and reinforcement learning. We have 3 speakers. You'll hear about them in more detail as they're introduced. Some ground rules, so to speak, are that people should stay on mute. There is recording of this session, and we intend to post the video. So this is being recorded. There is live transcription ongoing. Please feel free to ask your questions in chat. We'll cover as many of them as possible during a live Q&A at the end of each speaker's remarks. And then we'll save the chat as well. Hopefully they can answer further after their talks. And without, I should say thank you to Ms. Leslie Mosick and Lizzie Rogers for all the logistics and setup. And we have 4 great student co-organizers. Thank you for their help. And again, thank you to the Circuits and Systems Society for sponsoring this seasonal school. With that, David.
Okay, all right. It is my great pleasure. This is David Pan from UT Austin, and it's my great pleasure to introduce the first speaker this morning, Dr. Haoxin Mark Ren. He's currently a senior manager at NVIDIA Research, leading the design automation research effort. And he has been working a lot on machine learning applications in design automations, in particular for GPU and GPU accelerated EDA. Before joining NVIDIA, he also worked many years at IBM Microelectronics and IBM Research. So his work has been highlighted by NVIDIA CEO Jensen Huang at the annual conference. So he also published extensively and received best papers and so on and so forth. And he got his PhD from UT Austin in 2006, where I have the great honor to work with Mark. So Mark, the floor is yours. So Andrew, maybe you can unshare.
Yes.
So,
yep.
Mark, you can share the slides. All right.
Okay. All right. Is that on?
Yes. Yeah.
Okay. Great. Thanks, David, and thanks, Andrew, and all of you organizing this seasonal school. And I'm honored to be the first speaker to kick off this session. So my topic will be machine learning for EDA optimization. Let's get started. Okay. By the way, can you see my mouse? So I can point to things. Can you see my mouse?
Yes.
Great. So in this talk, I will cover 3 main topics. First, I want to give all of you some discussion motivations on why we are talking about using machine learning for EDA optimization. And then I will cover 4 more very important machine learning techniques that can be used for EDA optimization. Reinforcement learning is one of them. I will cover a little bit broader than just the reinforcement learning. And then I'll talk about how to integrate the machine learning and algorithms together. So let's start with introduction. As I work at NVIDIA, we build the GPU chips. And so we can see that over last 15 years, the size of the GPU chips become bigger and bigger. So start from maybe less than half a billion transistors in G80 chips. All the way right now, in the GH100 chip, we have 80 billion transistors. So the size will continue to grow. Even right now, we are at the reactor limit. We're going to have 3D chips in the future that will just grow up this continue scale this number of transistors. Now the challenge is the designs are built today with roughly 1 to 2 million cell blocks, and for each those of the design block, it will take more than a week of turnaround time to run through the physical design flow. So the problem with this very long turnaround time is the number of unique block count will skyrocket, right? Because our design size become bigger and bigger, and you have a constant block size. That means you have to increase your number of design block, right? As Samir Halepli point out, the design size and complexity relentlessly increase. The average size of block levels off, then unique block count skyrockets. And that will increase in demand of number of designers, number of servers, and number of EDA licenses. So it's a design resource has to also scale up, and that's a challenge. In the meantime, because the turnaround time is so long, we cannot make enough design space exploration to find the optimal design, right? Therefore, the design quality will suffer. And because of this long runtime, we cannot get early design feedback. So that also will make design quality suffer. So these are the main challenges, the scalability challenges today. And it's not because the current EDA tools are not great. It's just the problem is very hard problem. That's why let's look at why this is a hard problem, right? So a typical design implementation flow, right, have many stages, like from design planning, placement optimization, clock tree synthesis, clock tree synthesis optimization, routing optimization. And in all these stages, two main things happen. One is analysis, and another is optimization. Right? Analysis is very complicated. You have to be multi-corner, multi-mode, right? And optimization is multi-objective, like it's optimizing for PPA, power performance area. So optimization is very hard to do. So that's why usually it requires iterative optimization. And this iterative optimization will require iterative analysis. So that's why it's spending a lot of time going in between this analysis and optimization. And because of the runtime constraints, optimization has to make sometimes to meet the runtime constraint, it makes suboptimal results. Therefore, we consider optimization is the core problem of the flow, right? Because without optimization, this flow can finish very fast. That's why in order to solve the scalability problem, we need to rethink how to make optimization scalable, right? And let's look at the optimization problem in a little bit detail, right? So for EDA optimizations, conceptually, we can think about it as a mathematical optimization problem, right? Basically, you minimize some functions based on certain variables and subject to certain constraints. This is a mathematical form. However, there are some caveats about EDA optimization. For example, if you look at the variables of this problem, they're usually discrete variables, right? That means if you want to optimize it continuously, you need a relaxation of the discrete variables. Also, the dimensions of this optimization is very large. Usually have millions of variables. Let's look at the objective functions. sometimes this objective function doesn't even have an analytical form, right? For example, congestion minimization. And also it might take a very long time to evaluate, for example, the timing analysis, right? And that's why often people don't use the exact form, and rather they use approximate objectives, right? Such as violence, because you cannot estimate the violence directly, you use like half parameter violence. Of course, over the years, researchers invented many algorithms, like greedy algorithm, meta heuristics, nonlinear optimization, combinatorial optimization, mixed integer programming, network flow, so on and so forth. But because of the complexity of this problem and this problem with the variables objectives, these lot of algorithms are suboptimal. Right? For example, Jason Kong in like 2004 demonstrated that in placement benchmarks, they show a very significant gap from what the algorithm can achieve than the optimal. Okay, so how can machine learning help, right? I think machine learning can help improve the quality of results as well as scalability. These two things actually work together, but it's just a trade-off, right? If you have better QOR, then you can get a better scalability. It's just a trade-off. So what are my techniques we're talking about here? One is sequential model-based optimization, SMBO. And then there's reinforcement learning. Then there's self-supervised learning. Here I'm talking about generative models. And the fourth is the gradient-based methods, which basically means we leverage DR framework as well as architectures. So I will talk about these four techniques in detail. So let's start with sequential model-based optimization, or SMBO. Essentially, it's treated the optimization problem as a black box optimization problem. And you can sequentially sample, right, X from your data domain, your X domains, and evaluate its function value Y, right? You're sequentially doing this. And your goal is to find the optimal X, which give you the best Y with the minimal number of samples and evaluations. And how do you achieve that? Is by building a probability model of this objective function and use it to select the most promising data to evaluate next. So in the beginning, you initialize your data sets. So you create some samples with X, and it's a function objective Y, right? Let's say you keep K samples in the beginning, just a random sample. And then you train this model to basically predict Y from X. And this is usually trained with the Bayesian optimization. And then you inference this Bayesian model to find the new X K plus Y to sample. And then you evaluate this sample to get the true objective Y K plus Y. And then you add this new sample to your existing samples. And this process will iterate until you find all the samples you want to collect. So here's an example, illustrate how this works on a single input, single objective example. Let's say in this example, you have one variable X and one objective Y. And you read this red dotted line is the true objective function. And in the beginning, you have two evaluations. You have this point and this point. Then this model built with the Gaussian process will give you two things. One is it will give you a mean value prediction, right? This is a thick black line. And also, it will give you the variance, which is basically the uncertainties of this function, right? So it predicts the mean and the variance of this function based on the samples that you already have. Now, where do you sample next, right? You basically depend on two things. One is the uncertainty of your model, and the other is, of course, the predicted value of the model, which is the reward, right? So you want to pick points that either have high uncertainty, which is in the phase of exploration, or high reward, which is we call it exploitation, right? So you pick samples based on those estimates. And after, for example, 8 evaluations, now your model probably looks like this. You have new points sampled, and then your uncertainty estimations will be much better than before, because you only have 2 points in the beginning, right? So this is the basics of SBO. So let's look at the one application. For example, the flow parameter tuning, right? So when we show the design flow, they have many steps, and each step have many parameters. Here's the list of possible parameters used in this work. So the goal is to figure out the Pareto front, right? Because this is a multi-objective, for example, area and timing. We want to figure out this Pareto front of the PPA, given a number of different parameters. You want to find the best choice of the parameters that optimize the Pareto front. So as you can see, in this animation, initially you can random sample, right, from the parameter space, and this gives you some trade-off between area and the timing, right? So the area and the timing, and in the exploration stage, right, you build a model and you start to explore it. It will try to sample in the more uncertainty region, right? Regions that the model is not very known. So you can see it's starting to sample in a lot of places, kind of like randomly as well. And then later, when we go into the exploitation stage, the model starting to sample more on the Pareto front, because now we trust the model more, and we will sample these regions that we know is probably closer to the Pareto front, and you can see it's sampling more and more on the Pareto front, yeah. So this is a example on SMBO and it balanced exploration and exploitation. So my takes on SMBO methods. What's the advantage and what's the problem or issues? So first of all, these methods do not require gradients of the function, right? It's just the evaluation of the function. So that's a good thing. You don't have to have a computation and computable gradient. It is very easy to use. It almost always works. So this is it's a very good thing to very practical algorithm. That's why it achieved a lot of commercial success. For example, both Synopsys and Cadence have products built with these methods. Issues is it's limited to very small number of variables, usually in tens of variables, right? It usually cannot optimize hundreds of variables. And also it requires repeated evaluation of the functions. Repeated means in terms of hundreds or even thousands of evaluations. So if your function take a very long time to evaluate, then this could be a problem. Okay, let's move on to talk about the reinforcement learning. So I'm sure the other speakers will give a more in-depth introduction on reinforcement learning, but essentially reinforcement learning is just an agent work on make some actions for the environment, and the environment will give reward as well as its state information back to the agent, right? So reinforcement learning, why it can be used in optimization, right? That's a question. But if we look at the similarities between reinforcement learning and existing EDA optimization algorithms, you will find that it is actually very similar. For example, dynamic programming is a very well-known EDA algorithms. It is also doing this kind of planning thing, like our reinforcement learning, but the difference is for dynamic programming, it assumes everything, all the dynamics of the system is known. But for reinforcement learning, it doesn't. It also supports unknown dynamics. And then there's a simulation and linear or heuristic algorithms. And these algorithms are also close to reinforcement learning. It's just a different policy, policies for the actions. So similar linear use epsilon greedy policy, and the heuristics is just very straightforward, simple policies designed by hand. So reinforcement learning supports more sophisticated transferable policies. And then there's an evolution of algorithms, right? Like genetic algorithms. These algorithms basically using gradient-free an approach to optimize the agent. And reinforcement learning usually use some gradients. But the reinforcement learning is more efficient in optimization. So how do we convert the EDA optimization problems into a reinforcement learning framework? Usually, it requires a MDP process problem setup, right? It's a Markov decision process. So let's look at this minimization problem subject to constraints. One way to convert this problem into MDP is you can try to decide one variable at a time, right? So your actions is to decide to assign the variables for k at a k step, and then your states of that particular step is all the variables that are being assigned before. So from x1 to xk minus 1. So the next second way to convert the problem is to make some transforms. So the actions will be transform the states, the current states into a new states. So you have a previous assignment of all the variables, and then you can use a transform to make a change those assignment, all the variables at the same time. So this is transform-based approach. So either one, either formulations could work. Of course, you need a reward for the problem, and reward usually it is the objective functions as well as the constraints combined together to become the reward. And you have to also deal with partial assignment, because in the first case the assignment is partial. So how do you compute the objective and the constraints with the partially assigned variables? That's something you have to also consider. So let's look at the one example, which is the routing problem in standard cell. So here shows a standard cell, and all these lines are routes within the standard cell. And the red, these dotted red lines are DRC check-ins. Right? So when you're doing the standard cell routing, there may be a lot of DRCs. So we're trying to use reinforcement learning to solve the DRC problems. This is combined with the routing algorithm. So basically, we're going to search for the best routable candidates first, and then fix the routing candidates DRCs using reinforcement learning. So here's how it goes. In the beginning, we're using genetic algorithms to create a lot of routing candidates. And then we use maze routing to complete those routing candidates. But once it finished, you will see a lot of DRCs. And then we use the reinforcement learning agent to fix these DRCs, therefore to create a DRC-free routes. And of course, if the agent cannot fix those DRCs, there will be unfixed number of unfixed DRCs as fitness values returned to the genetic algorithm. As well as if the maze routing cannot finish routes, it will return unrouting nets as a fitness function back to the genetic algorithm. And genetic algorithms will use this fitness function to create a new candidate routes, and this process will iterate. So how do we formulate this DRC fixing problem, optimization problem as a reinforcement learning? Essentially, we can fix DRCs by assigning additional M0 metal grids one at a time. In this case, let's say you start with one metal here, and you found that there's 6 DRCs. we can assign additional medal, and that seems doesn't change the DLCs. But once you assign another one, it reduces the DLC by 3. And when you assign another one, then every DLC is fixed. So this problem is basically minimize the remaining DLCs after multiple assignment, right? And each assignment X variables is just a grid index for this particular assignment. So if we index the grid by X and Y coordinates of this grid number. So that's this optimization problem we're trying to solve, and we can basically decompose this problem as one variable assignment at a time. This is the first approach we talk about. Yeah, so essentially the action is adding additional M0 grid to reduce the DLCs. The state is the current layout image, and the reward is the DLC reduction. So we can see here we have rewards on different steps, depending on how many DLCs get reduced. So this formulation actually works quite well. The reason is a lot of these DLC patterns are local. They are local patterns. And this could be very well recognized by the reinforcement learning agent. That's why it achieved a very good success. It's been used in production for latest technology nodes. And we can see that compare, in a library, usually there's thousands of cells, and we can use NVCell to directly generate more than 92% of the cells. And it achieves very high quality. So compared to manual design, it is actually often smaller, which is better, and have a similar delay in the area, delay in the power categorizations. So this thing works. Now, my takes on reinforcement learning. I think there are many advantages of using reinforcement learning for optimization. First, it only needs reward evaluation, right? So it doesn't require the gradients to the reward. So as long as you have some reward evaluation, you should be able to optimize this function. Also, this is done with problem decomposition naturally. As we've seen, there's 2 ways to decompose the problem. So that's also a good approach. It can potentially create a generalizable policy for optimization. So unlike BOHB, which you have to sample from scratch for every single problem, reinforcement learning can potentially create a generalizable policy. And also it applies to very dynamic and stochastic problems. However, this is probably not the problems that in the EDA domain, because most of the problem we're talking about are static problems. Now, what's the issues, right? I think it has a very limited optimization variables. So usually it's hundreds of variables, because if there's too many variables, then your steps become too long and it become very difficult to optimize. Also, you require very fast reward evaluation. Usually it's like less than seconds. Otherwise, your runtime would be very long, and that's why that's the third problem. The training time of our reinforcement learning agent is hours or days because of this reward issue. It's also very difficult to generalize because each EDA problem instance could become like a new game, right? So these are my thoughts on reinforcement learning. Okay, that's why we're talking about a new approach. It's self-supervised learning. As Yang pointed out, reinforcement learning is like a cherry on top of the cake. And supervised learning is like icing on the cake. And self-supervised learning is actually the cake itself. And this analogy is based on how much information you can get from data, right? Reinforcement learning getting information from the reward only. Self-supervised learning getting information from your labels. The self-supervised learning getting information from the entire data, right? So what exactly it does? It's basically a training framework that try to predict hidden parts of the inputs. In this case, the gray part from the physical part of the inputs, and this is the green part, right? And the data inputs can vary from time to space. So you can predict some invisible, the hidden part of space, or you can predict the hidden part of the time, right? So that's the self-supervised learning. And usually they're being used to in two frameworks. One is the generative models. The other is representation learning. And for optimization problem here, I'm going to talk about generative models. We can also use representation learning capabilities of self-supervised learning for optimization, but that's not the focus of this talk. We're talking about generative models. So what is a generative model? Basically, it's a learning model that can generate new data instance from the training data distribution. What is the distribution, right? Let's say in this example, we have two-dimensional data. There's X and Y dimension data. And this is the density, this is the distributions of this data within these two dimensions. That's why we can always create a density estimation, the probability of X, right? Based on the data. And then the generative, once you build this density estimation function like this, then you can sample from this distribution to create a new data. There are many generative models. Here, let's just give one example, which is autoregressive generative models. Autoregressive generative models. It can estimate one variables at time. So basically, the density distributions of the probability density distribution for all the variables is the products of the probability of a variable t plus 1 given all previous variables, right? So essentially, it's deciding the variable probabilities one at a time, right? So it's the product of these variables one at a time, depend on it or conditioned on its previous variables, right? So this is one example where it's called pixel CNN, where you can try to predict the next pixel given the previous pixels, right? So you're predicting the red pixels given the blue pixels that's already been predicted. So this is a generative model, autoregressive generative models. Now, how do we use autoregressive generative models for optimization? Essentially, you can just consider the optimization variable as a sequence and generate optimized variables assignment one at a time, right? So if your optimization problem has n variables, you can generate x1 first, and then given x1 generate x2, and then given x1, x2 generate x3, right? Until you generate xn. Now, optimization problem has configurations, right? Because there's each different problem is different. So this model needs to be conditioned on the configuration, right? So essentially, we'll generate x1 based on the configuration, and then generate x2 based on x1 and the configuration, right? So it needs to be conditioned on the configuration. So transformer is one method, right? Transform model is one method to do the conditional autoregressive generation, right? So if you look at the transformer, it has an encoder, it has a decoder, and essentially you enter a sequence getting into the this encoder, and this encoder will create a condition embedding for the decoder, and in the decoder you will get you'll generate one token at a time, right? So this is a translation, like from French to English. So in the decoding, you'll generate the first token, and then use the first token to generate the next token, and so on and so forth. And they are conditioned on these conditional variables from the encoders. So it's not just generated random sentences; it's generated sentences that's conditioned on your inputs in this. So here's the detail of the transformer, right? It has multiple transformer blocks to be the encoder, and also have multiple output as a decoder, right? the key thing I want to point out is this multi-headed attention, right? This is self-attention logic, which allows a model to associate each token in the inputs to the other tokens, right? Where the attention weights. That means the each token is seeing information from all the other tokens, right? It's seeing the global information. Unlike a convolutional network, it only sees convolutional kernels that have a very limited scope. So let's talk about the one application of this model is gate sizing, right? So if we propose a combinational gate sizing problem as a sequence generation problem, right? So let's look at the timing path from sequential logic and primary input to another sequential logic, which is primary output. You have multiple gates, and each gate is kind of like a token or a word in a sentence. So if we collect features for each gate, then we can using this as the inputs to the problem, and our output is a sequence of gate sites. Right. So essentially, this become a translation problem. Right, you translate a sentence of gate features into a sentence of gate sites. Now the transformer self-attention become very useful because the gate size of each gate on this critical path depend on each other, right? So that's why the information sharing or this attention mechanisms on transformer can guide the determination of the gate size because they determine they are based on each other's information. So here's the architecture of this this model. Basically, we will send the features of each gate into the encoder, and then the encoder will go to decoder, and for decoder we'll start with the first gate type, and then predict the first gate size, the second gate type, and go to second gate size, and so on and so forth until we decide all the gate size. Here, an important variable is called this effort level. I'll explain what is the effort level, why it's used as a condition variables for this decoder. Effort level is defined as the delay of the median path delay over the actual path delay. It's a matrix to measure the trade-off between timing and the area power. Because the same path can have many different sizing solutions, depending on its timing and area trade-off. You can size all the gates very high to have fast speed, but you have to spend a lot of area. Or you can make everything very small, but then the path will be very slow. So this number basically represents how fast and how slow is the path. And here's the distribution of this effort level on a design. And you can see this effort level basically span from 0.26 to 2.5. That's the range. Now, what do I mean? The DM, right? The median path delay. It's just the sum of the median final for delay values of all the gates on the path. Right? This is once the path is given, this median path delay is given because we can always categorize median final for delays of all the gates. And the DA is the actual path delay. This is in the training, it is the optimized path delay, right? So in training, we are going to train with optimized netlist. And then with an optimized netlist, the path delay is optimized. So we just directly take that data from training. During inference, we don't know what is the optimized path delay. However, we have a target path delay because our for static timing analysis to meet the timing, it needs to be at least faster than target path delay, right? Which is the cycle time, right? And you don't want it to be too fast because if it's too fast, then you are wasting power, right? So that's why you just choose the cycle time as your inference actual path delay, and that's why in inference you can actually compute this effort level as a conditional variables and send it to the model. So with this method, we have seen that it's achieved very good results. So if we just de-optimize the netlist to reduce all the gates to the mean area size, and then run this transformer-based methods and compare it to a commercial tool to doing the sizing. We can see that the timing is very comparable after both tools, but the runtime is much faster with transformer. The reason is that on transformer, we can do 512 paths at the same time. So with a batch inference, and we can actually do a bin search that's basically also increasing our search scope. That we can even achieve like more than 1,000x speed up than what the commercial tool can do. So my take on massive speed up. My takes on the self-supervised learning or generative models. I think first advantage is there's no need to compute the objective function to do its gradient anymore, right? It doesn't even need to compute the object function because it assumes the data already give you the optimal solution, right? So don't need to do all of this. And its inference is very scalable, right? Because it doesn't need to compute the object function at all. However, the issue is that it requires a lot of optimized data to train it, right? I propose a data collection challenge. And you have to deal with outliers because no machine learning model is 100% accurate. So you might have some outliers that's unoptimized. So you have to be able to deal with those outliers. Okay, so the last methods I want to talk about is the gradient-based methods. And I'll use the nonlinear placement problem to illustrate these methods. So nonlinear placement algorithms usually is trying to minimize a function, which is include two components. One is the violence component, right? The violence of a number of cells and their XY positions. The other component is the bin overflow, right? Because you don't want the cells to be stuck in the same place, and that's create a lot of overlap, or that's illegal. So we call it overflow of all the cells. So these two functions are dependent on X and Y position of the cell. So in gradient-based optimization, it updates the X, Y positions of each cell using the gradients of this function over X and Y. This typo, it should be Y here. During this optimization, you can see cells getting moved because X and Y are updated over the gradient optimization process. This is very similar to neural network optimization, right? So neural network is trying to minimize a loss function given the weights and the data X, right? So it's optimizing the weights, but gradients is on the weights, and it's called a back propagation, but essentially it's just computing the gradient, right? So there's a very good similarity between this nonlinear placer and the neural network back propagation. That's why this placement problem can be solved with the DL framework. Because first, DL framework support nonlinear optimization problem with the gradient descent algorithms. And DL framework can scale to multiple CPU and GPUs. And we can simply formulate optimization objectives in terms of like building tensor operators or even build a custom product kernels within this DL framework. And it will increase the development efficiency because it's written in Python and not like C++ if you don't know to. So initially, we did a TensorFlow implementation of a nonlinear placer, right, and achieve a 33x speed up. And later we work with David's group at QT Austin and implement the gene place, which also achieve a significant speed up over replace, which was speed up CPU-based placer. And that's implemented on PyTorch. Right? So basically, both TensorFlow and PyTorch can be used as optimizers for this problem. And there are other frameworks out there that can be used as well. The second gradient-based methods I want to talk about is PPA-driven clustering. And here, we're not just using the DL framework to train, to optimize, to perform the gradient-based optimization. We are also leveraging the machine learning architectures, in helping the gradient-based methods to solve some immediate problem. So we all know that cell clustering helps PPA. If you have the right clustering as a constraint, you can as a constraint for a commercial placer, it will usually help the PPA at the end. So the question is, how do you come up with the cell clustering strategy? Yeah, it's to optimize how to find the best clustering solution. Now here we can use GNN, right? We can use GNN to compute the clustering probability matrix. This is the Q matrix, which basically has a row number of cells and and also a column of number of clusters. So this is basically assignment, the probability of which cell to be assigned to which cluster. That's your this is the matrix we want to optimize. So essentially, we start with a GNN. This is a basically a graph of the cells and their connectivities. And then using GNN, we can learn embeddings on each node, right? So V is the number of nodes. You can have embeddings learned on the GNN. And then you can predict its probabilities matrix from this embeddings. This is the probability matrix that you want to predict. And once you have that, we can formulate differentiable loss functions to approximate the PPA. So what do I mean differentiable loss functions? These are the loss functions we are trying to optimize. Basically, it's a multi-objective because it's a PPA. So we can have congestion loss, we can have timing loss, we can have power loss. And also because it's clustering, we need to have clustering loss and a similarity loss. So I won't go into detail of how all the loss functions are created. For example, I just want to show like one example and give you a feeling of why this is differentiable. Essentially, for congestion loss, we're using the probability matrix Q, right? And the C is the congestion numbers of each cell. So before this clustering flow, there's the estimation of each cell's congestion already. So with that, this QT times C produce a vector of what's the average congestion for each cluster, and the entropy maximization here is trying to make the congestions of each cluster as equal as possible. Right, because the entropy max means the probabilities gets equally distributed. Right, so this basically saying I want to distribute my congestion as smooth as possible over all the clusters. So with this loss, this whole computing graph is differentiable. Right? So that's why we can basically using gradient descent to optimize the GNN weights. Therefore, once the weights are optimized, this embedding is determined, and the probability matrix is determined as well. And once it's determined, we can just sample from this probability matrix to come up with the clustering solution. And in the end, it seems to have a very good timing and violence improvement with this gradient-based methods to create a clustering solutions for people for placement. So my takes on gradient-based methods. Advantage is it supports very large scale optimization. So we can support millions of variables easily with GPU acceleration. It is a very grounded optimization because it is optimizing for an objective, and we are using the gradient. It is scalable to multiple GPU platforms, and we can come up with leveraging ML architectures such as GNN to help leverage the problem inductive bias. Now the issue is, of course, it requires a differentiable objective function, right? Without objective function, you cannot compute a gradient. And a lot of problems are discrete problems, but this differentiable problem only solve continuous variables. So there's a relaxation of discrete variables required. You can also think about this gradient-based methods as a form of unsupervised learning, right? For example, solving the clustering problems, it is unsupervised learning because it doesn't require any label at all. Okay, now I want to switch gear to talk about the last section, which is the compare the machine learning model with EDA algorithms, and how do we integrate them, right? So, of course, EDA algorithms and the machine learning algorithms, they all have pros and cons. So for EDA algorithms, it's very good at solving an abstract problem, right? Very efficiently. However, the con is sometimes it's oversimplification, right? The complex problem gets simplified, so it's actually might not be solving the right problem at the end. On the machine learning side, it basically can solve any problems by learning from its data, right? However, it's to rely too much on data, right? It's not leveraging the mechanics of the problem. So there's pros and cons on both. And the idea is to integrate them together, basically using both machine learning and EDA algorithm together. And the key is problem decomposition, right? Key is the problem decomposition. And I want to use this framework proposed by Bengio, Yoshua Bengio, in his paper on machine learning for combinatorial optimizations, to frame this integration scheme. So there's 3 integration schemes. The first one is end-to-end learning with inductive bias. Essentially, when you have an EDA problem, you want to use machine learning to directly generate a solution. Now, how do you use EDA algorithms? Essentially, you're using EDA algorithms to generate the data to train for the machine learning algorithm, right? Just like a self-supervised learning methods. Here, the key is to leverage the inductive bias, which is basically the assumption preference about the function space, right? To help reduce the data requirement. Basically, when you design the machine learning model architectures, make sure you understand the underlying inductive bias of this particular problem. For example, CNN models has a shift equivariance inductive bias, right? When you shift something, it results the same in CNN. In GNN, it's the equivariance over relationship between entities and the environment to permutations, right? So these are the properties that's inductive bias of these models, and you want to, when you have your EDA problems, you want to make sure you're using this inductive bias in your design framework. The second way is called a coarse grain integration, which basically means when you have problem, you use machine learning algorithms to generate some inputs for the EDA algorithms, and then let the EDA algorithms to actually come up with the solution. Right? Machine learning generate inputs for EDA algorithms. There are at least 2 kinds of inputs you can generate for machine learning. One is the configuration parameters for the EDA algorithms. The previous example we talked about, parameter tuning, is one example. Machine learning only generate parameters for the EDA flow. Second way is to generate some additional constraints as the inputs to the EDA flow. For example, the clustering constraint we talked about previously. That's basically as a constraint generated for the placer. Right? So basically, the machine learning generates some constraint, and then the clustering constraint will guide the EDA placer to do the placement. And third way is called a fine-grained integration. Right? It's basically machine learning work alongside with EDA algorithms iteratively to come up with a solution. So here, the example I talk about is this cell routing problem. So we have traditional algorithms such as genetic algorithms, maze routing, to come up with routing candidates. And then the machine learning is kind of trying to fix the DRCs out of this routing algorithm. And there's both conventional algorithms and the machine learning algorithms work together to come up with final routes, final solutions. So when you think about everything I talk about, I think that my way of thinking about the machine learning for EDA optimizations is this. So this is my strategy. So given a problem, if let's say first we ask it whether it has gradient or not, whether it has a gradient to the optimized objective. If it has a gradient, I think we should just do gradient-based methods because that's the most efficient way. And if it doesn't have a gradient, then we need to check how many variables it has. If it's not many variables, then we check whether it can be evaluated very fast or not. If the function can be evaluated very fast, yeah, you can use reinforcement learning, right? If the function cannot be evaluated very fast, then you probably want to think about sequential model-based optimization, right? And if the number of variables is very large, then we need to check about whether you have optimized the data or not. If you have optimized data, then you can use these generative models as self-supervised learning methods. If you don't have a lot of data, now problem is very hard, right? It doesn't have a gradient. You have a very large number of variables, and you don't have data available. Now you need to think about problem decomposition, right? And basically, some of the problem probably have to be solved with conventional algorithms, and other sub-problems can be solved as a machine learning. And then you come back to the loop to decide how to solve the sub-problems. So that's my strategy. Yeah. So at the end, I want to talk about this new EDA computing paradigm. I think essentially hardware determines what kind of software you can write, right? It's the same for EDA. So in the beginning, in the early 1980s, people are building custom hardwares, like they're building these machines just for EDA applications. So it's like custom software on custom hardware. Later on, Intel had many generations of CPUs, single-thread CPUs. So EDA algorithms are all single-thread CPU-based algorithms. After 2005 or 2006, there's a multi-core CPUs available, and then EDA algorithms become parallel CPU-based algorithms. Right? Nowadays, we have GPU and a very nice GPU and CPU integration. Right? This is a great hardware superchip where there's a 72-core ARM CPUs and the largest GPU work together along each other. This kind of hardware will enable new paradigm of computing. Right? We're going to have parallel CPU algorithms, GPU accelerated algorithms, and the machine learning models to work together. And all of this can work on cloud. Right? So that's the new EDA computing paradigm, I think. Okay, so takeaways. EDA optimization shall be made more scalable to meet the increasing design size requirement. We outlined 4 machine learning methods to make EDA optimization better and faster. There's a sequential model-based optimization and the reinforcement learning. Both improve QOR are very difficult to scale. We have self-supervised learning methods and gradient-based optimization methods. Those are more scalable. Now, I propose 3 paradigms to integrate machine learning with existing algorithms, end-to-end, coarse-grain, or fine-grain. And at the end, I think the future EDA computing paradigm will include algorithms plus CPU acceleration plus machine learning model. And I want to leave you with this thought, right? So in Jensen's GTC talk, he talks about scientific computing can be accelerated million x by accelerated computing, which is GPU computing. And then you can scale out, right, with multiple GPUs, cluster of GPUs. And then on top of that, there's a machine learning model that can speed up further, right? So high potential million x. Now, my question is, can EDA optimization scale 1000x, right? We seem to see some number like 1000x in our application mentioned earlier, right? So can this be universal? So we can make the entire EDA optimization problems much more scalable, and which will enable us to design much bigger chip and a better chip later. And with that, that's end of my talk.
All right, thank you very much for your very insightful talk. And I especially like your overflow chart, right, to put all these things together. and give a lot of suggestions. So we do have quite some questions from the audience. Because of time, maybe we'll exercise a couple short questions, right? So one of the question, I think, from one of the, okay, you can see the chat there, right? I think it's about gate sizing, right? So how about those gates on multiple paths, right? I think your algorithm can handle that, right? Can you elaborate a little bit?
Oh yeah, so right now we're doing batch inference. So if a gate is on multiple paths, then it might be inferenced multiple times, and we will basically pick the one with the smallest size.
Right. There's another question from Chris. Yeah, there are actually a bunch of questions. I hope maybe you can stay even after your talk. Right?
Okay, sure. Yeah, I'll do that.
And I don't know, you want to pick one question to ask, answer now, or let's see.
Trying to see.
There's a question about reinforcement learning, right? Do you treat optimization questions as an episode task or continuous task, which is non-episode? So how do you choose a stopping criteria? I guess there are a lot of detailed questions here.
Which one are you talking about?
Oh, there's a question from Chris Lee, right?
Chris Lee.
Actually, for reinforcement learning, do you treat an optimization question as an episodic task or continuous task? Yeah, those episodic tasks. Yeah. In the formal case, how would you choose the stop criteria and what strategy? Yeah. So I mean, if you have a fixed number of variables, of course it will stop when the number of variables gets like iterated over. But if it's like transform kind of episodes, then it's deterministic, right? So usually you use some down signal, right, from the policy, right? So the policy can generate a signal, a particular action which is like down, right? Like, and then the environment will finish. So you rely on that to stop the environment.
Oh, okay. Thanks very much, Mark. Yeah, because we are running a bit late, but yeah, please, yeah, if you can answer that through the chat, that would be great, right? So,
sure, I'll do that.
Andrew will introduce the next speaker.
Thanks so much.
Andrew.
Okay, it's my great pleasure to introduce Ismail Bustany. You can see him on screen. He's a fellow at AMD, and he works on physical design implementation and ML-CAD. He's served on the technical program committees for ISPD, ISQED, and DAC, and he was the general chair of 2019 ISPD. He's also very well known for some seminal organization of contests in our field, especially for routing-driven placement and detailed placement. His interests include physical design, computationally efficient optimization, ML-CAD, sparse matrix computations and accelerations, and partitioning algorithms. His bachelor's, I'm very happy to say, is from UC San Diego, and his MS and PhD are from UC Berkeley. So Ismail, the floor is yours.
Thank you, Professor Khan, for the wonderful introduction. Let me share my screen with you. Let me know when you see it.
You see it in non-present? Yeah, perfect.
Okay, great. Yes, so I was asked by Professor Pan and Professor Khan to give a tutorial on learn to optimize paradigm. So I'm going to offer a perspective on it. Obviously, in 1 hour, you cannot cover the depth of the field, but I'll just give you a glimpse and hopefully excite your interest in it so you can, after this talk, read more on it and look at the references in there. All right, so let me start. So the outline of my talk is I will define what is L2O, which is learn to optimize. I will compare it with classical optimization, and I will focus this talk on the continuous version of L2O, in particular to solve continuous optimization problems. And I will ask the question, does it work in practice? And we'll see. And I'll give a snapshot of nascent L2O applications in our field. And then I'll give conclusion and future works. So let's start with what is. And so L2O is actually it's a nascent field. It's only in the past decade it has taken off, but its origins really are from I would say more than 2,000 years ago. It involves itself with the question of metacognition or meta learning. And if you look in Wikipedia, metacognition is defined as the awareness of one's thoughts, processes, and the understanding of. So it's basically reasoning about reasoning itself. Meta is, I know it's a company, but actually it goes beyond learning. So that's what meta means. And metacognition can take many forms, basically reflecting the way we think and the way. Sorry, let me just remove my screen here. Okay. The way it's the way one reflects on the ways of thinking and knowing when and how to use particular strategies for problem solving. And the goal for meta learning is to learn some general knowledge about the learning process that's useful across many tasks. And I will explain what tasks mean in our domain. And unlike ordinary learning, generalizations across tasks, not instances of a particular task. So it's a higher level of learning than just learning something and then applying it to solve a similar problem. Right? So these are the taxonomy of learning to learn. So there's actually this is I borrowed this slide from Kay Lee, who was at UC Berkeley. So there is the learning paradigm is what to learn, which model to learn, and how to learn. And if you look at the first category, which is what to learn, this involves itself. Oh, can you hear me? Hello? Okay. Yeah. So the first paradigm of what to learn, it involves itself in learning something useful about the algorithm that transfers across many tasks. So applications of that will be multitask learning or few-shot learning or transfer learning. The other category, which is learning which model to learn, it pertains itself to a particular task, not multiple tasks, but it's just a single task. And can you optimize the algorithm parameters to improve its performance on that single task? And their parameter optimization has taken off lately in that area. And then there's the purpose of the content of this talk is about how to learn. And basically this involves itself in learning what is it about the optimization algorithm patterns that one can learn to apply it to solve unseen tasks, really. How can I develop an algorithm that will work on a particular task, and when given with a new task, it can actually solve it. All right. So the L2O term was recently coined in 2016 by two papers that coincidentally appeared almost at the same time. One from Berkeley and one from Google DeepMind and Oxford University and Canadian Institute for Advanced Research. The one on the left, they both tackle the same problem. Basically, how can I use optimization? How can I use ML as the optimizer? All right. So the one on the left use a paradigm that's based on RL guided policy, and the one on the right use a paradigm that's based on LSTM, the recurrent networks, neural networks. And I will focus most of my talk on the paradigm on the left, because empirically, it has shown a lot of promise, although they're both great, but I'm presenting them to you here both. I just can't cover both of them, but I would invite you all to actually read those papers and learn from them. There are a lot of good nuggets in both works. Yeah, so the definition of L2O basically is to learn not what the optimum is for a given problem, but how to find it. All right, and then since those two papers, there's been a flurry of works. There's a very nice primer on basically a survey on learning to optimize, which I invite you all to read it. It's very thorough, and it covers a lot of work since then. And it tries to establish some connections. Most of the work in L2O really is not reared in strong theory because it's still a nascent field, and the topic is difficult. But this survey will show you some works that try to bring up more theoretical aspects for L2O and how to bridge that gap that we have right now. All right. So there's some nomenclature to cover when you talk about L2O. There are two main ones, the notion of a task distribution and the notion of a base model. A task distribution refers to the problems that we are solving and the data that's surrounding it. So typically a problem has parameters and has data, and that's what the task is to solve that problem given its data and parameters. So an example of that would be something like a linear program. The parameters of a linear program are the matrix, the constraint matrix A, the right-hand side B, the objective coefficient C, and the dimension of the problem N. And the data is basically X, right? And if you want to vary, if you want to vary the task, you can vary basically the parameters or the data. This will give you different task distributions. And base model in this notion, in this field, really refers to the algorithm or the learned optimizer that's going to work and discover patterns about these tasks and learn how to solve them. So like Newton's method would be something with parameters like gradient, Hessian, step length, and you'll see there will be parallels of a Newton method in our domain. We call them learned optimizers. And the way they treat the algorithm, they these learned optimization algorithms, they try to basically emulate or replace some part of the parameters in traditional optimization algorithms, be it the step length or the search direction. And that's kind of the paradigm. You try to replace them by learning those parameters rather than computing them through an edict or through some mathematical rigor. So here's the goal. Basically on classical optimization, we have a bunch of library of algorithms. We present them with particular optimization problems and we solve them. In the L2O paradigm, we teach or train a learner to solve a certain optimization problem or a certain task from a particular task distribution, like an LP, and the LP can have different sizes or different parameters from A, B, and C. And the learner, the job of the learner is to search through a space of optimization algorithms, so that's a space of optimization algorithms, and return a learned optimizer that efficiently solves the problem from the similar task distribution. So the goal really is it's not a panacea of solving everything, but you give it some task distribution. Let's say it's an LP, and you focus the teaching on solving an LP. You vary the parameters of the LP to have a wider distribution, and then you would hope that this learned optimizer, if presented with a new LP with different parameters, it will solve it. And the goal of L2O really is, can we solve that problem more efficiently, say, than from a convex LP solver like primal dual method or simplex? That's really the goal. All right. So the question is, why do we need L2O? You know, we already have a lot of theory developed through analysis and real analysis on algorithms and with a lot of rigor. So why even entertain the idea of using L2O? Well, the reason we need L2O is because we haven't solved the Holy Grail problem. The Holy Grail problem is to find an algorithm that will solve a non-convex optimization problem. And the best we have so far is an algorithm like Newton's method or its derivatives, like the quasi-Newton methods or first-order methods, that will get us at best a local minimum. And maybe the local minimum is not really a good local minimum. So we have still a gap in our optimization algorithms. That's one reason. The other reason, even in problems that are convex, depends on the conditioning of the problem. Some algorithms, if you don't precondition the problem well, they will take a while to converge. In fact, sometimes they can diverge. The hope in L2O is on those convex problems, the learned optimization algorithm will find some patterns from a particular task distribution, and then find some shortcuts to solve those task distributions of problems. So basically finding some shortcuts that will outperform the convex classical optimizer algorithm. So that's the hope on the convex side. And the non-convex side is, can we find better local minimizers through these learned optimization algorithms? There has been, like I said, a flurry of recent work over the past decade or maybe decade and a half. And the initial results are promising. For instance, if you look at LASSO, the least absolute shrinking and selection operator, which is basically solving a quadratic program with sparsification. And that particular problem, there has been, I mean, we already have ISTA and FISTA, which are iterative shrinkage algorithms. That the FISTA one, the fast version, works very fast actually. But even for these very fast algorithms that solve LASSO, we've deployed L2O to solving them. And as you can see from these plots, we can actually outdo FISTA. FISTA was up until then, the fastest known algorithm to solve the LASSO problem. So now, like I said, this doesn't solve it for all instances of LASSO problems, but for a particular LASSO distribution of parameters, you can tailor your learner to solve them faster than FISTA. And even sometimes we introduce noise in the system, in the parameters of the optimization algorithm. The learned optimizer can behave more robustly. So it has shown benefit, and the applications actually now are spreading to fields beyond optimization, applications like in computer vision, black box optimization, medical imaging, signal processing, and so on and so forth. And there's a very, like I mentioned, this survey, actually, I encourage you all to go and read it. You'll see some applications and more taxonomies of these L2O methods. Okay, let me just quickly go over classical optimization versus L2O. So I come from that domain, from the classical optimization domain, really. So there we are reared in rigor of theory, like real analysis and control theory, Lyapunov functions. And the algorithms are tailored for, like I said, we specify them for problems types, not data. So for instance, we can have an LP, QP, ILP, SOCP, LASSO, like I mentioned. And on the data side, we specialize them to be sparse or non-sparse. And then we devise algorithms that will solve these types of problems individually. All right, and now the learned optimizer, however, is different. You presented a sample problem like an LP, you vary the parameters of the LP, you train it offline, which in a very time-consuming process, and then with more data, with more parameter variation, its performance improves. And no proofs, no formal proofs, but it will improve and sometimes will give you better results. The building blocks for classical optimizations are steepest and gradient methods, Newton's method, simplex from Danzig, conjugate directions, momentum like from Nestrov, and Lagrangian duality, and etc. The building blocks for L2O methods, it's mostly, I would say, it's an MDP, it's a markup decision process, RL, and then also a lot of new techniques borrowed from machine learning itself. Like neural networks, in particular recurrent neural networks like LSTMs, and most recently generative adversarial networks, or GNNs, and graph convolution networks. And then it's a virtuous cycle. When you solve these learned optimizers, if you look through their inner core, at some point they need to solve an optimization problem themselves. So they also, one of the building blocks is all the stuff you see on the left. And probably more on the stochastic nature, the stochastic version of the ones you see on the left. All right, like I said, most of the classical optimization methods have strong proofs, certificates of optimality for rate of convergence and convergence. L2O methods, for the most part, rely on they're empirical results, and there are no provable guarantees. There are strong arguments why some of them work, and a lot of, I know researchers in the audience are working on bridging this gap, but I think we are not quite there yet. All right, and like I mentioned in the beginning of my talk, for convex problems on the left, convex optimizer, classical optimizers can find global minimum, and for non-convex problems, they find as a local minimum. For the L2O methods, we hope that the convex problems can be solved more efficiently. And for the non-convex problems, we can solve them, we can find better local minimum. So maybe we can approach the Holy Grail. All right, so now I'm going to focus the talk on L2O. Now, L2O really applies to both combinatorial, discrete, and continuous optimization problems, but the focus of this talk will be on continuous optimization problem, partly because that's kind of where that's my really domain. But I encourage you to look at the other domains from that survey paper. Okay, so if you look at the continuous optimization problem, and this is the algorithm template. You're minimizing a function, and in this case, I'm not going to say this is constrained, or just think of X as belonging to some compact constraint set. So this applies both for constrained problems and non-constrained problems. So you're minimizing this function over X, and this the algorithm typically has an initial data, X sub 0. You compute a search direction, and then you compute a step length, and then you do an update in step number 3. Where you take the search direction, you do some kind of step length on it, and then you do the update, and then you do a test for optimality. And then if you're optimal, you stop. If you're not optimal, you recur. You keep iterating until you stop. Typical algorithms for these methods, like I mentioned, H can be the gradient method, or it could be the search direction can be Newton's method, or it can be Nesterov, and there are many other flavors. All right. The paradigm shift here in L2O is, instead of computing the search direction and computing the step length, we learn the search direction and we learn the step length. That's it. Really, that's in a nutshell what L2O is for continuous optimization. So somehow the learned optimizer needs to learn both the step length and H, the search direction. Sometimes actually it doesn't make a separation, it just learns the search direction. So the step length is embedded in that search. Okay, so the question is, what kind of tool sets do we have to use for solving these, for training those L2O? So the first tool that comes to mind is supervised learning. And the question is, can we use supervised learning as our L2O learner? Can we teach this learner using supervised learning methods? And you'll see the answer actually may not be quite right there. So there are two observations that are basically that at every time step in the optimization trajectory, the iterates are independent and identically distributed. Or the other assumption is that the dependence of future observations on the current observation for the iterates is unknown. In our optimization algorithm, the choice of the step length impacts future search directions. So whatever, if you do a line search and you find some step length using, let's say, Armijo step length or with the wolf condition, these step lengths will have an impact on the future search direction. So that doesn't quite jive with assumption A1. And then the impact of alpha on the future search direction is unknown. How does it change the search directions is not something we really know. The problem with supervised learning is it's because we give it sample data points. It assumes this. It kind of tends to assume knowledge of the local geometry of the unseen objective function. So when presented with a function it hasn't seen before, all it has to learn to rely on is the past objective functions it has seen. So it will see some pattern in the objective function that is at hand, which is unseen. It will say, oh, I've seen this pattern before on one of those objective functions I was trained on. So I'm going to guess this step length and this search direction. And so really it tends to generate search directions and step lengths that are based on its memory of the past objective functions it has seen. And this actually is a problem. So it's a well-known problem. And the problem is the following. If the optimizer, the learned optimizer, which has been trained in supervised learning approach, encounter a function, an objective function geometry locally that it hasn't seen before. It will get rattled a little bit. It will say, oh, I haven't seen this quite before, but I'm going to guess it's maybe like one of the patterns I detected before. It will present you with a step length in a search direction that is a little bit off trajectory. And then because it's off trajectory, the function will not be minimized very well. And then the next iterate will see something that it hasn't seen before because the function geometry was not seen before. It will generate yet another wrong step length and search direction. And it will keep producing those wrong step length and search directions along the trajectory. Eventually, it will diverge. And this problem actually is known as the compounding error problem. And for supervised learning, there's very nice work by Ross and Bagnall in 2010 that shows for supervised learning, if you use them as for learning, the divergence is quite extreme. Actually, the error rate, the cumulative error rate grows quadratically. So like here, I'm just showing the demonstration. This is actually, I borrowed this from Jonathan Bushnell. Sorry, I didn't credit his name on it, but basically, like, imagine you have a racetrack, and the optimization, you're a driver, you're a car race driver, and your optimal strategy is to follow this expert trajectory. And if we're trained with supervised learning, eventually you see a curve maybe on a different racetrack that you haven't seen before, and you make a small maneuver that's off. And that off maneuver, you see a different curve in the road, and then you keep going off and off. Eventually, you'll basically have a crash. And that's what happens with these supervised learning approaches when we try them. So the answer is no. We cannot use supervised learning to train an L2O optimizer. Can we use RL? I mean, like I said, you can also use LSTMs, but I'm going to focus this talk on RL. So I would invite you to look at the plethora of research on using LSTMs. Just for the shortness of time, I'm not covering it, but let me introduce you to this approach. So can we use RL? And let's find. So just a quick primer on RL. RL, there's a set of states, set of actions. There's a probability density function, initial probability density function, and there's a state probability density function. There's a cost function or a reward, depending on which capital of the world you are from. And then there's a time horizon for the control, for the policy that you optimize over. And the policy basically is a conditional probability density function over actions given at an observation at the current point in time. So it's conditional. So the policy does not give you this action that you take, it doesn't tell you take action A, like steer the wheel in this direction. It tells you steer the wheel with probability 0.8. Will get you a good reward. So really, that's why it's not just like an answer. It's a probabilistic answer for the policy. And the goal in RL is to learn an optimal policy. And learning an optimal policy means the expected reward or the cost, like in this case, expected reward over time is maximized, or in the other sense of the word, the expected cost over time should be minimized. All right, and and then there's one crucial assumption in the RL. So let me just, before I go to RL. So when we talk about, about this property, when we talk about optimization really is a sequence of iterates and actions, which the actions would be like the step length and the search direction that the optimizer decides. So it is this trajectory. And if you think of the world of RL, then if we have any recommendations from RL, it will give us kind of a recommendations for this action, and it will give us probabilistic recommendations for the action. So this induces kind of a probability on the trajectory that the RL-based control will take. So there's always a probability density function associated or implicitly implied in the trajectory itself, because the RL policy will give you a probabilistic measure. It will not give you like, take this action, like I said, it's a probabilistic measure. Okay, so the interesting thing, our property of RL is that it does not know this probabilistic PDF. It actually, the job of the RL algorithm is to find the nature of the dynamic of the system that it's trying to model. So the PDF distribution is actually learned. It's not given to us. So there's this notion of model-based learning or free model or model-free based learning. RL falls in the kind of the model-free. There's no dynamical model that you are aware of when you are doing RL. You are learning that model. Okay, and that's actually a crucial, it turns out to be a crucial assumption for us when we are using this as an optimizer, as a mechanism for optimization. So the empirical answer, and I say empirical because there's no proofs in our domain here, RL actually does work as a learner. The fact that it does not assume an assumption of this PDF or the dynamics of the this trajectory that minimizes this objective is in its favor, because during training, the conditions of training and testing are actually identical. The RL assumes no knowledge of the objective function local geometry because it doesn't know the PDF distribution of it, of the trajectory. And because of that, when it sees something when it has an unseen objective, again, it doesn't make any assumption about its local geometry. It will basically just try to use, if it finds something it hasn't seen before, it has its probabilistic measure of recommending the action, and that will help it kind of adjust itself if it sees something that is quite not what it saw in training. So that's really the power of RL. It's basically, it does not make any assumption about local geometries, so it does not tend to overfit like in supervised learning. All right, but like I said, there's no proof. This is an argument, and we think it works empirically, and that's why we use it. And if you look at the LSTM approach, similarly, there's a similar argument there. Basically, it's an unrolling of an optimization problem as a sequence and the recurrence, and that's why they use LSTMs. But again, it's a similar argument. There's no proof. So how do we do the transcription from a continuous optimization problem to an RL-based optimization problem with L2O? Basically, we define the state as the iterates, the functions, and the gradients. The policy will basically be a guided policy that learns the search direction and the step length, and the action in this RL scheme is basically just the update step. And then there's a slew of those guided policy techniques. Now, when I say guided, let me just quickly introduce you for those in the audience. I'm sure a lot of you in the audience know what that means. But since this is a tutorial, let me just quickly tell you what I mean by guided policy and how you compute it. So if you look at the trajectory of optimization, so let's denote the trajectory for the iterates as a sequence of controls or these actions and the iterates themselves. And that's the policy that we are generating with RL will basically generate those actions or these controls. So now remember, the policy itself is probabilistic. So and it has some parameters like any other policy, and let's call these parameters theta, like is denoted here. And then because the policy itself is probabilistic in nature, it has a PDF, it will induce, like I mentioned, a probabilistic density distribution on the trajectories themselves. So based on which of the recommendations that we get from the policy, based on that PDF that the policy generates, our trajectory can have different trajectory actually, right? Because it's getting these recommendations probabilistically. Yeah. So like with any control problem, actually trajectory problem here, there's a time horizon. So over that time horizon, this is what the PDF of the trajectory looks like. So you start from a position x sub 0, you apply the policy at that position, it will give you some control, some action u of 1, and that will take you to the second iterate, second state. And then you see that second state, you apply the policy on that second state, it will return to you some probabilistic recommendation for which action you take. You pick which of those actions is the most probable, and based on your pick of that most probable action, you will move on in that trajectory. So that's the PDF for the trajectory. So how do we compute the gradient of that policy? So let me just define what's the objective here. The objective for us over that time horizon, we want, this is the cumulative reward. So I'm going back to the other camp of the world where we think of maximizing reward as opposed to minimizing cost. So let's define the reward over all the trajectory points as the sum of all these rewards on the trajectory. And the goal is in RL is to maximize the expected reward over that time horizon, over this PDF that's induced by the policy, the PDF of the trajectory. So to make things cleaner, let's define this this expression, call it J, this function. So you just basically want to maximize the parameters of the policy theta to minimize this cost, the expected reward over time. And the beauty of this really, and maybe I cannot cover this very thoroughly here, but you'll see something really amazing happen. When you compute the gradient of that cost function, the reward does not depend on the parameters of the policy. So really, when you take the derivative with respect to the PDF of the trajectory, the PDF of the trajectory, you can do some trickery in here. You'll find that the PDF of the trajectory does not depend on the dynamics of the system itself, but rather on the dynamics of the policy that you choose. So I'll show you like in the next slide what that means. So by some math trickery, a simple thing, you can just convert this to an expectation over the log of the gradient of log of the PDF of the trajectory. So basically it's expectation of this function. And what's interesting here is the gradient of this this PDF of the function really is just the gradient of the policy, of the guided policy. So you can choose whatever policy distributions, like most of us in this world and in this application use kind of Gaussian distributed PDFs. And then these have either closed form derivatives, or in the case of machine learning, this policy will be basically a neural net because it can model the dynamics of the unseen space or the unseen objective function, and you can compute the derivative by backpropagation. Yeah, and this is why the reason why this only depends on policy, because if you look at the definition of the trajectory PDF, it's basically the multiplication over time for the conditional probability with times the policy. And that's, you know, if you take the gradient of that, becomes the sum of the logs, the gradient of the logs of the policy gradient. And that's how actually we compute it. Yeah, and then so the prescription really is this: you how do you compute those gradients? You for that along the trajectory for the PDF, you have some initial guess for the policy. You start it with some initial parameter, and then you run it. You over time, you observe where the state is. You apply an action. You compute the gradient by that scheme where you just the formula I just showed you, and the formula can be either done if you have a model-based policy. You have a closed form expression. If you have a neural net-based policy, you get it through backpropagation, and you just keep recurring. And that's basically how we do this with L2O. So we get the gradients. When I said we learn those gradients, you really get them from taking the gradient of the policy itself. Okay, does this work in practice? So I will harken back to the initial work by Kay Lee and Jitendra Malik. I'll show you their results on this from their seminal work in 2016. So does it work on convex problems? So in this case, what I'm showing through their work is a logistic regression problem, and they defined some parameters for it. And they trained it on let's say 120 objectives, and then they have about 200 unseen objectives. And if you look at the results, the one in green right here, this is the predicted L2O learned optimizer, and they have this thing called mean margin of victory, which means basically how better are we than sorry, they are comparing this also with gradient-based methods, momentum, conjugate gradient, and LBFGS from Jorge Nosdal. And then they want to see how better, how lower the function value as they progress through the trajectory. And the lower it is, this number should be higher. but you can see it actually right here. So on two examples, you can see that the learned optimizer for a convex problem converges faster. So like around 18 iterations in this case, and around maybe, especially on the one on the left, it actually does converge faster. The one on the left, I think LBFGS converged faster, but the fact that it actually does something there is promising. So on some problems, it does show that it does work. So that was their initial finding. Here's kind of a visualization of what happens. If you look at these two-dimensional versions of that logistic regression problem, these methods, some of them converge fast on some, maybe depending on the conditioning of the problem. Like for instance, LBFGS sometimes converges in 10 steps, sometimes in 26 steps, sometimes in 2 steps. Maybe in this case, the preconditioner worked very well. But the interesting thing about the L2O, it's pretty much robust across those problems. Like it takes 5 steps in all of the cases. So it's as if it has found some kind of magic recipe and it's just following it. And it's not that it's intuitive for us to see what that recipe is. Like in this case, it overshoots and then comes back. Or in this case, it undershoots and then comes back to the trajectory. Sorry, in this case, it overshoots and then it comes back very quickly. Yeah, so, but it's kind of, the behavior is not something quite expected from a typical classical optimizer. Classical optimization, as you know, they kind of tend to be conservative. We just walk, unless you have the ultimate preconditioner, you go like in one shot, or you're lucky. But they tend to be very conservative, while the classic, the L2O seems to be taking some shortcuts somehow. Does it work for non-convex problems? Again, they took a robust linear regression problem. This is non-convex in the parameters W and B because of this denominator. And again, they trained it on like 120 objectives, and then they gave it 100 randomly generated unseen objectives. And the way they do this is, like I said, with task distribution, they vary W's and the B's, and also the size of the problem. And there as well, so the prediction here, if you look at it, is this green. The L2O optimizer is the green one. And again, actually, it does it does give you a better solution. This now, remember, this is a non-convex problem, so there's a local solution, local optimum. And it turns out for this robust linear regression problem, a lot of those for the unseen test cases, the quality of the local minimum is better. And this is what you get from it. And in fact, for some of them, for some of the other methods, they even diverge. Like I think in one of those cases, let's see which one diverges. It's the conjugate gradient. I guess we didn't have a good preconditioner there for it. Yeah, so that's kind of the promise. In the convex realm, they can converge faster than the best algorithms we know. And then in the non-convex realm, they can give you a better local minimum. The question is, can they solve a high-dimensional problem, not just baby small examples? So this is again from a later work by Kaylee and Professor Jitendra Malik. In 2018, they sought out to solve, to basically use an L2O to train a neural net. And the neural net they picked was fully connected, 2-layer. It has 48 inputs, and likewise 48 two hidden layers with 48 hidden units, an output of 10. And there are some bias units, but they didn't tell us what's the bias in there. And then they trained on MNIST data. These are like, the digits, right? Very simple data. And then they tested it on completely unseen data. So now what they are doing, they're having dissimilar task distributions. They are like the distribution, initial distribution was MNIST, and then the test data is not MNIST. They're not testing it on same task distribution. They're varying the problem. Again, they will test it on neural nets, but the data that they are feeding the neural net is different. So remember, like there are 2 ways to vary the task distribution. You can vary the data. Like remember my example for linear program, I can vary the data itself to have different task distributions, or I can vary the parameters A, B, and C. So what they are doing here, they're varying the data itself by having different benchmarks, like they're using this Toronto faces images. These are grayscale images, not numbers. And then these are the CFAR 10 and CFAR 100. They are color images with different variations in the number of categories of objects they see. So they're really varying the task distribution quite prolifically here. The question is, can the learned optimizer work on these unseen examples? So they did 4 experiments. In the first experiment, they used a similar architecture of the neural net that this learner is training. Now, remember, they're using a RL guided policy, like I mentioned before. And there are a lot of details which I'm not going through here, but I encourage you to look to read their paper, how they did it. So the upshot is this. If you look at this trajectory right here, this is the learner convert. This is the iteration count, and this is the cost. For the learned optimizer, it's actually doing better than most of the other ones. Conjugate gradients actually diverged. LBFGS is not doing great. This blue one right here is the method that I mentioned, the parallel method based on LSTM, the blue one. And this red one here is the RL based one. So on the those 3 benchmarks, the CFAR, the Toronto face detection, and the CFAR 10, CFAR 100, the learned optimizer actually is doing better than all of the other ones as far as the performance. It converges to a better solution faster. So that's good. But this was easy because we use a similar architecture. So we didn't vary the parameter of the task distribution. Now they are varying the parameter of the task distribution, not just the data. And by doing that, what they've done is they took, instead of 48 input, 48 hidden units, they took 100 input, 200 hidden unit architecture of that fully convolutional neural net. So now they have really varied the task distribution. The question is, does it work? And you'll see, like on the TFD, the Toronto face detection, it struggles a bit, but eventually it converges. And same with the CFAR 10 and CFAR 100, it converges. The LSTM one, for some reason, actually didn't converge. Yeah, and the other ones obviously don't converge as well. So, I mean, the interesting thing here, this is you are using ML itself to teach an ML neural net, right? How to optimize it, and that's what's amazing here. All right, and then in the training set, when they train this optimizer, they train it on a period of 40 time horizon of 40. And what they've done here is they made the time horizon longer, and even though they made it longer, it can actually also detect that. It can do very well. And then let me see. The last one is, what if you introduce noise in the system? Introducing noise means, like, when you take the stochastic gradient, the batch count should be smaller, as opposed to taking, let's say, a batch of 1,000, take a batch of 100. Or, like in this case, instead of having a mini batch of 100, I think they took batches of 10. And again, most of them struggle to find any solution. The learned optimizer also in the beginning diverges. But like I said, because it doesn't know anything about the PDF or the dynamics of the system, somehow it compensates and somehow it finds better solutions. Again, it's not a certificate, but you can see its behavior. The quality of the solution is much better than the rest. So in a nutshell, empirically, they do seem to work, these L2Os. There are many nascent applications in our field, in MLCAD. If you look over the last 5 years, I would say, I mean, Mark listed many of the works that he and his colleagues and people in the field are doing. So like in standard cell placement, macro placement, Azalea and Goldie's work, similar work there for macro placement. There's very nice work from Betts and Kevin Moray in University of Toronto, I believe, on improving their simulated annealing FPGA placer with using an RL guided policy. In ASIC routing, there's very nice work from Carnegie Mellon that shows they can use RL guided policy to solve. Sorry, they use a DQN. It's not RL guided. So I think people have not used RL guided policies in routing yet. There's some new work, but yeah, I'm just listing one of the DQN works, which is yeah, it's not RL guided, but we are actually working there. Lala Behjet and her students are working on exactly that on the RL-based guided policy, and hopefully we'll see that work coming soon. In FPGA synthesis, there's deep learning as well, approaches there. And then if you look at MLCAD, DAC, ICCAD, I mean, many of us were in ICCAD this week. There were a flurry of works on RL guided policies for end-to-end optimization. In fact, I know for instance, in ICCAD, 1/4 of the submissions were in this realm, in this area. Okay, and then there's some nascent work on combinatorial L2O, which I didn't cover. Okay, I'll quickly run through this. So like, for instance, there's the macro placement work from Google, and there what they've done, they took 5 units of their TensorFlow, 5 blocks, and they've optimized them. They optimized the macro placement for them through an actor-critic RL guided policy network. And it was inspired by their AlphaGo Zero approach from DeepMind. And they trained it on really 5 TPU units, but they took about 10,000 sample placement. So they varied the parameters of the placement, and then they generated 10,000 samples. In their work, in Anna and Azalea's work, what they did there, they optimized the location of the macros one at a time. And there was like, I think about maybe 100 or 200 macros in each one of those TPU blocks. And then with every, and then they use a force-directed placement to judge the quality of the reward. And that was actually very time consuming in their approach. And I think since then they have sped it up, but it's still rather time consuming. So it takes actually days or weeks to train, maybe days in Google, since they have TensorFlow units. But the interesting thing is, as we all know in their Nature paper, the quality of results will beat the manual placement, right? So it shows really high promise. And this was not zero shot. They still have to do some kind of training online. So it's few shot training. So what this is showing you is like here in this case, this is the few shot training. The green one is the few shot training. So as opposed to training it from scratch, with few shots, like within a couple of hours, you can get actually like 5 hours, you can get a decent network, an L2O optimizer, quote unquote, that will solve the macro placement for you. Okay. All right. And then there's very nice work from Sang-Hugh Lim, not for end-to-end optimization, Sang-Hugh Lim from Georgia Tech, and his student Agnesina. Yeah, sorry, I don't know his name, but I think he is in Cadence, I think, now. Okay. So their approach actually is very nice. Also, they use an actor-critic network again to optimize parameters of the Cadence Innovis placer. And they use a combination of GNNs and spectral properties of the graph, and they use an attention network in their actor-to-critic policy. And then they show really interesting results. In fact, in their approach, it's a one-shot. So what they do to get the one-shot, which I thought was very novel, is they have the policy, they give it an input for the placement, and they have the policy generate kind of scenarios for the, so you give it a placement and you run it through the policy itself, and the policy will generate recommendations, and you feed those recommendations back to the inputs, and then until it stabilizes, and then they pick the solution as a one-shot. And just by doing that, without running any few-shot training, they actually can beat their commercial level tool. In this case, actually, it's a multi-arm bandit that they are comparing it with, and you can tell it's much better with the RL versus the human. Obviously, the multi-arm bandit does better, but the RL guided one does even better than the multi-arm bandit. Okay, and then there's some very nice work in FPGA test configuration. In FPGAs, we have these switch box matrices, and we need to test them. And then what they did there, if you look at the switch matrix, there's some kind of transition function that you have to describe when you go from one pip to the other. And what these researchers did, they basically described the state transition function from the switch matrix box description from the device model, and then they implicitly defined an MDP process, and then they use an RL policy to do the the learner on it. And it was actually really good work because the number of test configurations in their learner was almost like 9x fewer test configurations with coverage than the best known work up until this time. That's yet another application of L2O. So I'll conclude. So I covered motivation recipe for transcribing continuous optimization problems into L2O learner framework via RL. Like I said, there are other approaches like LSTM, which we call in the field unrolling an optimization algorithm. I would encourage you to look at that in that survey paper. Then the RL guided policy empirically shows better performance both in convex, it can converge faster, and non-convex, it can give you better local minimizers. The scalability of L2O, like we saw with the Google work and many other works, many of our, us as practitioners, when we work on them, we don't have the luxury that Mark has in NVIDIA, but they do. Thanks to Mark's work actually and NVIDIA's work, we can solve them faster. But we do need a strong powerhouse, a power horse to solve these problems. So we still have some work to improve on scalability, even though it was demonstrated, like I said, in this work on the teaching a neural net how to optimize it with an L2O. The number, if you look at, I didn't mention that, but the number of weights that they were optimizing in that work was about 1.2 million. So these L2O minimizers actually work for high dimensional problems. They really work very well. It's just that training them takes a long time. And hopefully with Mark's work and, with Cerebras doing and Google TensorFlow and AMD and Intel, hopefully all of us collectively in the work of Andrew Kahn and Professor Pan and Telos and the community at large will get faster ways of solving these problems. All right. We're really in the MLCAD world, we're still in the early innings, but we have some nascent applications that are showing promise. And there's a lot of growing research to bridge the gap between theory and empirical results. There's some mentions of that work in that survey I mentioned. And then there are some really interesting extensions, like also Mark mentioned, the work from Bengio in combinatorial optimization. I would encourage you to look at that because our problems are combinatorial in nature. And I think there will be benefits in looking at those approaches as well. With that, I conclude my talk. I'll take any questions.
Thank you, Ismail.
Thank you.
Well, I know David will take over at some point, but we have a few questions in chat and a few minutes to go over them. Can you see the chat, Ismail?
Yes, so let's see.
Okay,
the dimensionality of, shall I just go?
Sure.
The dimensionality of the optimization problem changes. Is there any other chance than retraining the optimizer from scratch? Yes, so actually, yeah, there is. So what's interesting, what I showed you there, like in the problem with the neural nets, right? The neural nets training, they did not really do any. It was like zero-shot training in there, right? They just used the learned optimizer in zero-shot mode without without retraining it. You can do transfer learning. That's the what, the learn what to learn. You can do obviously transfer learning to improve it. But the promise of L2O through its RL approach is maybe you don't really need to. Like the work of Sankyu Lim with the parameter optimization also indicates that you probably don't need to do that as we think. Or if you need it will be very few shots learning. Okay, what about robustness to changing properties of the objective function? For example, small additional input noise. Is there a difference in using on-policy versus off-policy algorithms for L2O? Yeah, so off-policy, like DQN, for instance, is off-policy. I don't think they are very robust. Maybe researchers in the audience will answer this better than myself, but we like to do on-policy because they are adaptive in nature. And like I said, they will predict the PDF distribution of the geometry of the objective on the fly. So I have a bias for on-policy gradient approaches rather than off-policy, just for that fact, because you can't really see, you can, like a DQN, you have to kind of store it in a lookup table. And what if you didn't give it enough sample distribution, or task distributions were not very diverse? Then you're kind of stuck and it can diverge. So I think on-policy ones are usually more prevalent in our field, I would think. Yeah. Is there a possibility to parameterize the optimizer in a way that it learns specific optimization strategies for the problem? For example, different types of neural net architectures it's seen. Maybe the type of problem could be used within the RL state as an input. Sorry, is there a possibility to parameterize the optimizer in a way that learns specific optimization strategies? Okay, so maybe what you're saying there, yeah, there is. So I didn't touch on it very much, but there's this thing called, I mean, there's this approach called model-based L2O, and there, exactly what you said, instead of just having no assumption about the dynamics of the system, we give it a model of the dynamics of the system, and we try to change the action of the policy will be to change the parameters of that system that you gave it. So, and that's basically how you do it. So, and we call this model-based learners. So I give you some model of the system, not zero knowledge, and I train the optimizer to improve upon the parameters of that model. Like the work from SunQLM I showed was something like that. You know, he really was just, the placer was the model, and he was just improving those parameters of the model by the learner itself. Should I take more questions, Professor Pan and Professor Khan, or shall I?
I think Ismail, you did a great job. It was kind of a one-on-one with Peter, it seems, all three of his questions, and he already put his thank you into the chat. And I think if you could stay on a few more minutes to catch anything that comes up in chat, that would be great.
Sure.
But thank you again so much.
Thank you all. Thank you so much for inviting me.
Yeah.
Thank you very much.
I think if you stop sharing, then David will take over with the introduction of Joe.
Yeah, sure. Okay, our next speaker is Dr. Jiang from Google Brain. And Joe is currently a staff software engineer and manager at Google Brain. And his research interest is to apply modern machine learning to computer systems, and of course, recently chip design, including physical design, floor planning, chip placement, and routing, and also hardware RTL verification. So he has been working on the chip trainer project, which actually the team that actually published the Nature paper last year. And so he will talk about the trick trainer, circuit trainer from Google's Brain team. And so he also, that part has been made open source, and he will also maybe do some demo. And besides on working on chip trainer, circuit trainer, he also co-founded the design to verification RTL learning method for verifying hardware designs on TPU. So he held a PhD degree in computer science from Princeton. So Joe, you're there?
Thank you, David.
Okay, let me unshare and you can share.
Let me share my screen.
All right, awesome. You're sharing, I guess.
Can you see my slides?
Yeah, you can put it in the full presentation. Yeah, okay, works great. Thanks.
Cool, thank you. Yeah, thank you. Good morning, everyone. I'm very excited here to talk about our work on the circuit training. And thanks for the previous speaker who has, give a very brief overview of our, RL work for the chip placement. And today I'm going to, talk about, give a more detailed overview of the work, and also hopefully do a quick demo to demonstrate, how we train this distributed RL applications. So, and by the way, I'm Joe. I'm from Google Research and Brain team, and I'm, this is a joint work with many people at Google from both research and the TPU design team. So, in the past few decades, we have witnessed an increasing trend of demand for compute over the years, and the year 2012 is likely a watershed year. And before that, the amount of compute is roughly doubles every 2 years. And since then, the amount of compute used in the largest AI models roughly doubles every 4 to 3 months. And there are more and more newer models that's introduced every week. In comparison, the Moss Rose has 18 months doubling periods. So which likely is likely to catch up with the demand of for the latest AI compute. So that means that we not only have to design more powerful chips, but also we need to accelerate the process of the chip design. So this shows a kind of an end-to-end life cycle of the chip design process. And in this work, we're particularly focusing on the physical design step. So physical design still is a very human-intensive process today. And even in the production, like in TPU, it requires weeks or even months of time from the human experts to iterate on the physical chip layout until it reaches the production quality. And also, these experts not only need to be the expert in the physical design, but also need to understand RTL very well, so they can do a good floor planning. And our goal in this project is to use reinforcement learning to quickly generate the layout and attain human placement quality. And the key here is about it has to be fast. So this is in contrast to the human iteration that takes weeks or even months. So reinforcement learning, before applying it to the chip design space, it has been well applied in other areas, such as playing computer games or board games. So probably the most famous example is AlphaGo, which uses RL to solve the Go game and win the human champion. So usually the reinforcement learning works very well in these kind of applications when you have a very clear reward, such as win or lose, and also involves a sequence of decision making here. So the question we ask ourselves is, can we use a RL agent to play the game of ASIC chip layout? So this doesn't seem a complete crazy idea, because placing these the nodes on the chip is similar to playing a Go game, where you need to play these chip components, including macros and standard cells on the chip. And also you have a very clear reward, for example, in terms of wire length, timing, power, etc. However, chip placement is a much more complex problem than the Go game, by merely just looking at the number of the states in the problem. So it's much bigger than the Go game. And also in Go game, you just have one rule, right? But in chip placement, you have different kinds of chips, different using different technologies, which further complicates the problem. So what I'm going to talk about today is mostly focused on what we have published in the Nature paper last year. And in this work, we demonstrate that we apply the reinforcement learning based methods in the production TPU chip placements. So up to date, this solution, RL-based solution, has been applied to the 3 generations of GPU chips. And the placements that are generated by the RL solutions are taped out and fabricated. And I believe for 1 generation of the TPU has already been deployed in Google's data centers. So just a quick overview of the chip placement problem. So here we're mostly focusing on the macro placement problem. So the task here is to place these chip components on this 2D silicon canvas. So there are 2 types of chip components. One is called the macros, which represents the memories, and these smaller nodes, which represents the logic, which are called standard cells. So the number of macros is on the order of like tens or to the hundreds of macros for modern chips. And there could be millions of standard cells. So the goal here is to place these nodes on the 2D canvas in order to minimize the latency of computation, and also with power consumption and chip area, etc. While meeting the design constraints, such as the congestion and cell utilization, etc. So this is a very typical graph resource optimization problem. And to solve this problem, like what typically human experts do is they start with some seed placements, and then they just move the macros, around and iterate it for a very long time. And part of the constraint here is that because for every new design, they have to evaluate using the EDA tools, which takes sometimes days to finish. So this greatly limits how much different designs the human experts can explore. So just in contrast, in production, for every day of time to market delay, it costs X million dollars of efforts in terms of the operating opportunity cost. So if we can use the machine learning to quickly help the designers to come up with the better layouts, so this is together a huge opportunity. So the chip placement problem has been studied for many decades. So prior to the learning-based approach, there are other existing approaches. So there are, I think early in the days, there are these graph partition-based methods. And then we have the pure like random methods like simulated annealing, which performs stochastic hill climbing kind of search. And the state of the art of the algorithm lately is probably the analytical placers, mostly like replace or the accelerated implementation like dream place. So here we are trying to look at the problem from a different perspective. Is in addition to purely solve this as an optimization problem, can we also introduce some of the aspects of the learning into the problem? So here's some advantages of the learning-based approach. So unlike the traditional approach, which trying to purely solve this as a mathematical optimization problem and using search to find a good solution. So the learning-based approach is different. So first of all, in order for the learning-based approach to work, it needs to find the underlying relationship between the context and the target optimization metrics, and trying to build a model to find such connections. And with the learning-based approach, as the RL agent or the ML model sees more designs, it's trying to generalize all the knowledge after seeing more and more chips. So over time, this model is going to gain experiences over more and more instances. So in contrast to the traditional approach where these optimizations like, do a lot of search, but once they solve a problem, they immediately just, discard the knowledge. So which seems to be a waste. So our, the potential of learning-based approaches is going to generalize across different designs. And hopefully with that, we don't have to search from scratch. And this is the key where the learning-based approach is outperforming the traditional methods. And third of all, I think the opportunity here is that, with the general infrastructure of machine learning, you can train a very large models, with billions of parameters, with TensorFlow or other, the machine learning, framework. And also with the distributed platform, it enables doing a lot of this kind of, data collection, which is essentially doing the search. And this is a very generic purpose platform that was developed for, initially was developed for, solving other ML tasks. But it turns out to be a very generic platform for also solving this kind of optimization problems. So after showing these advantages, definitely there are, complexities that we need to overcome. So first of all, as I mentioned, the problem size is very large. It's much larger than the Go game. And how can we scale the RL agent design for such a large problem size was unknown. And second, in chip design, this is a multi-objective problem. So in contrast to most of these games, they either have a win or lose score, or in these kind of Atari games, they usually have a numerical score, which you can optimize. But in chip design, there are many objectives which are often competing. For example, the wire length and the congestion, they're often, kind of a trade-off. And for some of these objectives, like, the timing, which is even complex to measure. So one of the key challenges here is that some of these reward function is very expensive to evaluate. So some are easier, for example, wire length, and we likely have a kind of analytical form of the hub parameter wire length. But for timing and other metrics, usually we can only run the EDA tools to get the accurate measurement of these metrics. And if we fully rely on the EDA tool to get a reward function, it is too expensive. So for modern, like in the chip, if you run EDA tool to measure some timing, it easily takes hours or even days. So this is definitely not acceptable for most of the RO applications. So which also poses a challenge to us is, can we come up with a good proxy reward such that it's accurate enough and it's fast enough that can guide RO agents to search in the right direction. So this is basically the RO framework that we're using in our application. So this is a very standard reinforcement learning framework where you have an agent which generates actions, and then you have a floor planning environment where given the placements that are generated by the RO agents, it measures the proxy reward, including wire length density, congestion, and also in the latest version, we're introducing timing to this environment. So the RO, in our RO design, so we basically, we debate about, whether we should generate all the placements at a time, or we just focus, like playing the Go game, we place one node at a time. So it turns out that, so trying to place all the macros is quite challenging because it requires a very big network that tries to, have multiple heads to predict the node placement at the same time, which is pretty challenging. So we think of from a simpler, more straightforward design, which is we ask the agent to place one node at a time. And after placing one node, we can get observations from the current state. We can query some of the partial wire length and partial congestion, and then we can use the observation to guide our agent to make the next actions. So after all the macros are placed by the RO agent, so we also have other standard cells. And because the scale of the standard cells is just much larger than the number of macros, so we create a kind of hybrid approach, which we use the existing analytical placers to place the standard cells, given the macro locations they are suggested by the RO agent. So then, with all the nodes that are placed on the canvas, then we'll be able to, call the flow planning environment, and then to measure the proxy metrics for all the QR metrics we care about. So yeah, this is essentially basically the hybrid approach we're taking here. So in our application, we're using a very standard the RO algorithm, which is PPO. So this is a policy gradient kind of RO algorithm. And we also tried a few kind of other RO algorithms like DQN. Eventually, we found out this kind of policy gradient-based approach is the most reliable. And because essentially, at the end of the day, this is still an optimization problem, which is quite different from other kind of dynamic decision-making problems. So policy gradient turns out to be very effective in finding out the gradient direction against all the objective functions, which either has analytical form or can only be measured through the black box simulation. So policy gradient is very efficient in guiding the agent to search along the right directions. So also we talk about this multi-objective optimization problems. So in our work, we just and take a very simple approach, which is using a weighted sum of these objectives. And since the publication of the Nature paper, there are other work that try to do this kind of multi-objective exploration at the same time in the RO agent. So the RO can simultaneously explore the Pareto, the curve, and which takes the trade-off between the different objectives. But initially, we take a weighted sum of this approach, And then it requires some of the kind of, experimentation to get understanding, basically you're running experiments to figure out what's the overall, operating region of these, metrics. And then we define a threshold function to basically make sure that, we kind of treat these kind of congestion and density as a constraint rather than some objective you really need to optimize. So this is also one of the key that makes, the RO application work. So one of the key innovation in this work is, how to design the neural networks that's used in the RO agent. So in the PPO, there are two key networks. One is policy network, and the other is the value network. Policy network predicts the what's the next action, which is where to place the node on the canvas. So initially, we also tried many different approaches in the policy network, and eventually find out this deconv, architecture seems to be a good fit, because eventually you need to predict, a distribution of the locations for a node, where to place in the grid. So the deconv layer actually works better than the other kind of, the MLP architectures in terms of predicting the actions. And also, one of the key innovation here is the representation learning, which we find to be extremely important. So the representation learning means, like, given a netlist, how do you convert, the information of the netlist into some, learnable representations, some embeddings. So before that, we actually tried out some black box approach where, we don't have the graph neural network. So to some extent, the RO agent can still work, but it kind of overfit to a particular problem you give to the RO agent. So it can still optimizes the wire length, decreasing other metrics. But when you give it to another, new block, it doesn't generalize. And actually the solution is quite, random. So inspired by that, so we create this kind of, graph neural network and trying to learn what's the representations in the netlist graph. And because netlist is a graph, so the GNN seems to be a good fit. So and since then, this is the GNN is one of the key features that make sure that the RO agent that is trained on, the one block that can generalize to other blocks. And this kind of representation learning is also a very active research area. And I believe since then, people have proposed other methods to learn how to represent, the netlist graph in other models. So I'll give you a quick look on, what is the design by, this the RO models. So compared to, so basically here, this is I think one of the real TPU block. So from these images, you can see that these the blurred white areas represents the macros, and the green areas in the center represents the standard cells. So usually the human designers follow some rules, from their past, experiences. So their placements tend to be very regular. And for example, the macros are snapped to the boundaries of the canvas. So this is typically, the design rules that, the humans have in their mind. And on the other hand, the kind of ML-based placer finds out a smoother and more rounded kind of macro placements. And because this is a, kind of wire length optimization game, so that's why it's trying to find out this kind of more convex shape of the placement in order to reduce wire length. And so on the left-hand side, the human placement takes about, 6 to 8 person weeks to achieve to the final placement, because people need to, as I said, run the EDA tools and adjust placements and iterate for a long time. Whereas in the ML placer, we just let our agent generate one placement and send the placement to the EDA tool. And this takes less than 24 hours for our agent to generate the placement. And compared to the human placement, the wire length in this particular block is 3% lower, and also it meets other the routing constraints. So this is a very First time, like we found, this is actually the first block we found, it's outperforming the baseline placements. And since then, we have more other, designs that can achieve, the better wire length reduction. So what I have been talking about is the general set of the RL agent, which basically, given the new design, RL agent is trying to train a new block from scratch, right? And I think, as I alluded earlier, one of the key areas is to leverage the learning capability in the ML models and trying to generalize across different designs, so we don't have to search from the scratch. So like before the generalization, the paradigm is that given a new netlist, you train the new netlist from scratch, and the RL agent typically needs to take tens of thousands of iterations in order to converge and then find the best placement. And now with the generalization, the idea is that, okay, let's just send a bunch of netlists to the RL agent. And this agent is trying to optimize across all of the netlists at the same time. So the reward becomes kind of the average of this QOR metrics over all the different netlists. And then we train this for in the offline training, which again needs to take tens of thousands of iterations in order for the agent to converge the policy. And then for new netlist, we can just take the pre-trained agent. Basically, we load the model parameters from the pre-trained agent and then let it do the zero-shot inference or do the fine-tuning. So for fine-tuning, hopefully, we only need to take a much fewer number of iterations for the RL agents to arrive at the best solution. So this is one of the result that shows that the pre-training actually helps the RL agent's generalization. So if the RL agent trains from scratch, initially you see because the policy is started from random, which essentially randomly place the nodes on the canvas, so the quality is pretty bad. But if we have already trained agent through a bunch of other blocks, and then we see that actually even at a zero shot, it can achieve pretty good result. And then of course we still need to do the fine tuning in order for the RL agent to converge to the optimal result. So in this particular example, this is a RISC-V REM block. We see that if we train from scratch, it takes more than 24 hours in order for the RL policy to converge. But the pre-trained using the pre-trained RL agent, the convergence is much faster, which takes about only 6 hours to nearly converge to the optimal performance. And what's even more exciting to us is we found that actually with the pre-trained RL agent, the RL trajectory can converge to a different optimal point, which is better from training from scratch. So this is likely because typically for policy gradient algorithm, it's doing some gradient-based search. So it can easily get into stack of some local optimum, and this local optimum may not be necessarily good. With the pre-trained RL agent, because it sees many different blocks, so it likely has explored different local optimums from different blocks, and that is why the agent is able to drive the RL agent at the fine-tuning stage to a very different local optimal point, which can be better than the training from scratch. So we also see this generalization results on other the TPU blocks. So we compare the RL placers performance to the commercial tools, and also we plot out RL agent's performance on the zero shot and with a different amount of time for the fine tuning, and compared to the training from scratch. So in most of the cases, the fine tuning always wins compared to the commercial tools and also training from scratch. And what's I think very important to mention that basically selecting the training set is actually very important. So so far I think we show that the generalization can happen across different blocks, but also it's important to know that there might be many different kinds of chips And in this experiment, we're doing the the pre-training on a set of TPU blocks, and then we do the evaluation on another TPU block. And it's also an open research kind of question in terms of can we train a very generalized agent where it's just trained over different kinds of chips, and it can still generalize to the unseen kind of the chip or even the new technology. So that is I think it's the aspirational goal where we train one RO agent to place all the chips. So yeah, this is some visualization about the RO's result on the ARIAN block. So I think left-hand side shows the training from scratch, and the right-hand side shows fine-tuning. So every of the square block represents the placement locations of a macro. So if we train from scratch, you can see that initially this RO policy is random, so it randomly placed the nodes on the canvas. So the location is pretty random. But over time, it's trying to improve that, and then you will see that over time, the agent learns to leave a space in the middle, for standard cell cloud, and it needs to place the macros along the boundaries. And in contrast to the fine-tuning, even at the a zero shot, it knows to find out, leave a space in the middle for the standard cell cloud. And also keep in mind that, in pre-training this agent, it's pre-trained on other blocks that's completely, different from this block. But it's still amazing to find out the agent can learn, how to leave this, find this kind of geometric space in the floor plan, and knows to, leave the space for the standard cells. And finally, also, as I mentioned, this fine-tuning on the pre-trained policy likely is going to converge to a different local optimum compared to, training from scratch. So you can easily see that fine-tuning is also moving the locations of the central space, slightly moved a little bit in order to fit to this particular block. So this is what we expect to see, from the RO agent. So I think one of open research question is, can we really achieve the few shot learning, which is, instead of fine tuning for, a couple of hours, can we really doing the fine tuning just within a few steps, for example, like, under 1 hour, that we can achieve, the final optimal results. So, and if we can do that, then I think that would be a really a game changer. So to summarize our adoption on the real TPU block, so I think this is our last generation of the TPU chip. So on the TPU V5, we applied RO-based placement method to all of the TPU blocks. So there are 37 blocks that involve, have macros, and out of the 37 blocks, we have 26 of them that has better QOR than the baseline human placements, and the 7 equal and 4 is worse. So these QOR metrics are measured by the EDA tools to basically, given the macro placements, so the EDA tools is going to do its own standard cell placement and report the final timing and wireless and other metrics. So what's we want to mention is that, on the blocks that, currently the RO agent is still trying to, catch up with, is this kind of, so-called crowded blocks, where crowded blocks means that, they have a large number of macros. So the macro to the area ratio is very high. So in these cases, because it's very, busy, so the RO agent needs to simultaneously solve the placement problem and the packing problem. So these are the, at the time of, publishing a paper, these are the most challenging blocks for us for the RO agent to place. And since then, I think we have been doing some research and trying to tackle these crowded blocks problems. And we have made some exciting progress around that. So also, as I said, one of the, in this RO, one of the key kind of question is similar to supervised learning, right? It's about how do we make sure that we pick the right training data to make sure that when we do the the evaluation, there's no kind of distribution shift. So this is kind of a, I think, kind of overfitting is probably a common problem in supervised training. But overfitting is probably harder to detect in the unsupervised learning like RL. So we also did some experiments trying to see, okay, if we use different blocks to pre-train the RL agent, and how does it affect the fine-tuning performance? So in this experiment, for example, we compared to training from scratch or pre-training a diverse set of TPU blocks, or also pre-train the RL agent on the same block, but from the previous versions of the RTL, right? So in this case, we find that in most of the cases, I think pre-training a block, pre-training on the same block from the previous RTL version can actually show a better result than training on the the general TPU blocks. And this is not entirely surprising, because across different RTL versions of the same netlist, so the change is very small, right? So oftentimes, especially at the later stage of the design, this different netlist, the difference between the different netlist versions are very small. So in these cases, we should really reuse the the pre-trained RL checkpoints from the same block, but from the previous RTL versions. So it enables like better convergence, and also it can even converge to a better local optimum compared to pre-training from a general TPU blocks. But sometimes this is not entirely true. We also find there are some outliers where training on the general like TPU blocks is better than training from similar blocks. So overall in this space, this is a very, I think, interesting research question in terms of how can we make sure that we pick the right training blocks in order to achieve the best result. So even though we believe that in order to improve the generalization, for example, placing on the different chips, we need a very diverse set of blocks. But if you really care about the best result, so sometimes it's a open research question in terms of what is how to pick the similar blocks, or pick the enough with blocks with enough diversity in order to achieve better generalization. So this is a I think open area for research. So so we open source the entire RL framework that's published in a Nature paper, and we also we open source the entire RL code and the circuit environment code for estimating the wire length and other QR metrics on the GitHub. So since then, I think we have attracted a lot of interest from the research community and the industry, and so these results are fully reproduced and validated by our collaborators within Google and external research teams. And so far today, in production, we're running the same version of the RL code that's published on GitHub, and we use that to generate production chip placements. So a couple of feature highlights for this this open source RL framework. So first of all, this is a truly distributed training framework, which I'm going to talk about next. And this RL framework also supports transfer learning, which means that you can always train from scratch, but also you can use the framework to train the different blocks to get the pre-trained checkpoint, and then you can load the pre-trained checkpoint to do the fine-tuning. So this transfer learning is fully supported in open source code. So encourage, if you're interested, and tried out the transfer learning features in open source code. And talking about the distributed implementation of the RL framework, so this is one of the key, I think, which makes the RL, scales these kind of RL application and make it work on the chip placement problem. So this is a fully distributed framework where there are many components in the system. So like I previously mentioned in this, the very typical RL framework, you have these kind of environments which are actors. So the actors basically is responsible for generating the placement actions, and the actors will load and pre-train the or load the existing RL agent's policy from a variable container, which is essentially a mem cache, and it loads these policies and inference the policy network and generate actions. And these actors are deployed distributedly, can be deployed distributively on the cloud, meaning that they can run on multiple machines or running several jobs on a single machine. And then these actors are going to send all of these samples to a centralized replay buffer. So replay buffer is basically also a in-memory data store that basically stores all these the placement samples. And then the learner side will pull these samples from the replay buffer. Depending on the RL algorithm we choose, it can either be on policy or off policy. So depending on the requirement, it can pull the different, the samples, for example, whether it's going to pull the latest samples from the replay buffer or it samples the data using this, any in strategy that's decided by different RL algorithms. So this revert buffer fully supports that. And then the learner is basically a kind of also a distributed learning, that supports both GPU and TPU platforms. So you can also try to run this code in the open source, which I'm going to give a demo later, which shows that actually you can run a small scale of the RL run where you have all these jobs that's launched on your machine. But definitely, it should be super easy to scale this, to multiple machines, and you can pick your favorite cloud platform. So, as I mentioned, having a distributed implementation is also one of the key to make this work. So, essentially, having more data collectors is, essentially, increase the number of samples the RL agents can, explore. And it is expected to improve the performance, of the placement. So this in this experiment, we show like, how can we scale, with using more data collectors and using more GPUs for training. So here, see if we use only one GPU, so it takes more time for the placement to converge. And as we increase the number of GPUs, and also at the same time, we also proportionally grow the number of data collectors, we see that the convergence can improve, right? And but at a certain point, there's always a limit where having more GPUs or even more data collectors is going to plateau again, which means that, okay, for this particular problem, this is likely the limit of this, this is likely the amount of, I think, the sample search that is needed. But for complex blocks, you can always benefit from using more accelerators and using more data collectors. And also what's interesting is that it's using more compute not only helps with the convergence, but it also helps with the final optimal result, which is very interesting. So for example, if we use only one GPU, it can never, even if we let it train for, an infinite amount of time, it will never reach as good result as training with a GPU workers. And this is likely because with fewer compute, when RL agents is doing a search, it will likely fall into some local optimal point. And because of the, the nature of the policy gradient-based RL, so you will be stuck in there. And with more workers, so initially, the RL agent is able to explore more states and likely, explore many different trajectories to different local optimal points. And that is why having more workers, at least initially, is very important. it basically helps you to, search many, the agent explore many different trajectories and making sure that it does not always get stuck in a local optimum. So to summarize this work, before going to the demo, so with this ML-based like a chip placement tool, our goal is to allow our designers to quickly generate many alternatives of the placements. So in our production placement, we still allow the human designers to do some fine tuning on top of the RL-based solution, because they always have their own preferences, and sometimes with that then honor their kind of own kind of preferences. But using this tool, it definitely help them to improve the productivity, so they don't have to do this kind of manual exploration. And RL-based placement is a very good tool for them to explore different designs. And also some of the example is like it helps to avoid kind of time to market delays in terms of the late changes in the design. So typically, actually this happens in our production. So we have some last minute changes to the design. So using this RL-based tool, it really helps to quickly, close the last minute changes within a few days, which typically has to take, for a few weeks. And to broaden the scope of the of this kind of AI-based tool, our eventual goal is to move up to the upstream of the chip design cycle, such that we can enable the higher level explorations in the design, for example, in the architecture exploration, and only with ML2 based tool that helps you to quickly to get a fast, accurate estimation of the this QR metrics. You cannot do the high level architecture exploration. So our whole vision is that we need to enable use these tools to quickly come up with a good estimate with the different architecture choices, and help the designers or using AI-based approach to do the architecture exploration. So with that, let me move into the demo. So first of all, I'll give you a very brief introduction, on how to run the RL, framework that's open sourced on the GitHub, and then I will show you some of the, the results on how to look at RL, the results. So let me, before I go into the instruction, let me first quickly launch a tool. So, so this is a local RL run, which I create a script to basically launch all these different jobs. And it will take some time to warm up. And so let's wait while the job is running in the backend. So essentially, as I mentioned earlier, there are 4 different jobs in the RL system. So essentially, you have a actor, which is the data collector. And then we also have a reverb buffer, which stores these samples as well as the ML models variable, the parameter values. So they are co-located in this reverb server job. And there another job which is called the learner, which basically performs the training and then pulls out the samples from the reverb sub buffer. So in order to run this code, basically you can first of all you have to install the TensorFlow, and also with the TensorFlow the reverb server. So this is another kind of open source the code in TensorFlow. So you can download the code and also put out the repo in the circuit training. And so basically, in order to run this job, you can basically run them on the same machine. So here the instruction provides a simple example, like just running one trainer and just one collector job. So basically, you can run these jobs using everything is in Python, and you can run the command to basically run each of these jobs, independently. And the key parameters probably, that is needed to tune, is the number of episodes per iteration. So this parameter is defines how many samples we need to collect from all these different data collectors before we train the model and do a model update. So in this case, we have 16 episodes, right? And for each episode, it basically, as I introduced earlier, we're placing one macro at a time. So the total number we are collecting is the number of episodes times the number of macros in the design. So this is how many samples we're collecting in the replay buffer before we perform a round of training. And I think the other major parameters we can play with is the per replica batch size. So this is essentially in the training, which decides, what's the batch size when we do the model weights update. So usually a large batch size will help you to reduce variance, which means that it makes the PPO algorithms gradient estimation more accurate, and you will see less noise in the RO convergence trajectory. But of course, with a large batch size, usually, depending on the accelerator platform you're using. So if you're not using accelerator, large batch size, sometimes we can train more slowly. So let me move to the job. Yeah. So this is one of the job I just launched. So let me pause the log. So basically, you can see that these are basically the log information that all these jobs are, printing. So here you can see each of these messages collecting at step 0. So this is at the 0 step of the training iteration, right? And so far, initially, the worker is using a model with a ID 0. That means this is the initial model. And you can also see the collectors, this is based on the current policy. It takes an action. And then these are the key QR metrics these actors, reported. So for example, you can see that for every different worker, they're reporting different wire lengths. And this is expected because initially the RL agent's policy is, random, right? So essentially you're doing some kind of random placement on the canvas. So that's why you can see very different, the wire lengths that's coming out from the current samples. And then as we keep training, we see also after collecting enough number of samples, the trainer is going to, do a few gradient updates and update the policy. And then this loop continues, and I pre-populated, so, in this simple example, I'm only training with one data collector, which will take a long time to converge. So I have pre-trained an RO experiment with 256 data collectors, and it is trained on TPU clusters. So on the GitHub, they also provide instructions on how to launch the TensorBoard. But basically, there are 4 important sections on TensorBoard. So the losses, these are basically the metrics that are related to the RO algorithm, and in particular, the PPO algorithm. And the performance basically measures, how good it's measured. It keeps track of the placement quality, and keeps track of different QR metrics. So in the PPO algorithm, so there are a few key things to look at in the TensorBoard. So first of all, I think the most important thing to look at is the entropy, right? So when we play with the RO algorithm, so the first order, things we want to make sure that the RO is working is the entropy has to be decreasing. So this is intuitive because, entropy is just a measure of how, the random your policy is. And if the RO agent is really making progress, you should see that, the entropy of the policy distribution is getting lower. So this is one of the key information that we should expect to see, in training the RO, the agent. And there are also other couple of metrics that are, in particular, very important to the PPO algorithm. So for example, in PPO, eclipse the gradient because PPO, this policy gradient sometimes is very sensitive to the estimation of the gradient direction. So in PPO algorithm, we want to keep clip the gradient such that it doesn't, suffer from these kind of, initial noises, and to make sure that our agent can explore along the right direction. So from this metric, flash clipped, you can see, initially how much of the gradient, like, is clipped. So this gives you a sense of how noisy the initial kind of, gradient estimation is. And over time, we should see that, as the gradient converges, the amount of, the gradient becomes smaller and smaller. So the amount of clip should become smaller. And the next metric, the ground norm, is just a measure of the current the gradient estimation. And then this loss function basically tells you whether your neural model can overfit to the current data set. So in order of the training steps, you should expect to see that the loss close to 0. If the loss is not close to 0, that means that either the model is not, the model architecture is not good, which cannot overfit to the existing data, or some of the training parameters, such as the learning rate or batch size, has to be updated. So yeah, in all of these things stages, we should expect the loss to be 0. And these kind of performance is more straightforward. These just basically measures over time how much the performance is improved. So for example, in this block, wire length is one of the key metric we're looking. So we are expected to see the wire length decreasing over time, and also this the return curve. This is basically the RO rewards return. So over time, you should see the return improving over time. So yeah, during our development, there's a lot of problems initially when we design a new algorithm. So these are the key metrics to look at usually when you debug the RO application. And to be honest, like tuning RO application is much more difficult than tuning supervised learning model. But there are many, I think, newer researchers which basically like, especially from AutoML, some of the research also from Google, that help us to automatically tune the RO agent in a more efficient way, rather than doing a lot of this manual tuning on these RO parameters. Okay, I think this is I'm going to conclude with the demo, and thank you for attention. I think have a few minutes for the questions.
Well, thank you very much, Joe. Right, it's a great talk and a demo, right? So we do have a bunch of questions, and how about maybe you can see the questions, right, from the chat, right?
Yeah.
Yeah. So maybe you can pick a couple to answer, and well, actually, the workshop pretty much is done today, right? So we can stay a little longer if need. I'm not sure. Andrew, do you have any suggestion?
Oh, I think we should go with the Q&A as long as Joe can stay. That would be wonderful.
Right.
Thank you, Joe. That was great.
Yeah.
As always.
So the question from Shafing, do you do any form of masking in the output layer of the neural network? The action space is massive, and it makes sense to set some action values to infinity. Yes. So this is a kind of, in the output actions, we do a mask. So because of the nature of the problem, the macros cannot overlap. So even if the policy predicts you can place it a certain location, when you check the environment, it may not be legal because it overlaps with other macros. So this is a kind of like different from what traditionally this PPO does, because they never do masking. So we do the masking at output layer to make sure that we normalize the policy distribution only on the legal locations. So this is a little bit deviation from the traditional PPO, but it seems to work and it seems to converge.
May I ask a follow-up question or?
Yes.
So the checking of what actions are legal, this is very time consuming. To give you some background, I'm doing my dissertation on this subject, and I've come up with my own solution using reinforcement learning and graph neural networks. How do you compute what actions are legal quickly? Or do you just don't do it quickly and just take a lot of time and accept that that has to be an issue?
So for checking legal locations, so compared to the traditional kind of checking, you have to check n pairs of macro pairs, right? But in R, you don't. It's linear because when you place a new node, you just need to check whether it's overlapping with the existing placed macros. So it's linear time.
Okay, understood. Thank you for answering that question.
Cool. Next is the from Peter. Is the representation learning included in the overall learning process, or is it some form of additional learning task? Yeah, that's a very good question. So in this in the currently published work on GitHub, so the representation learning is done at the same time. I mean, we do this pre-training. We do the pre-training on a diverse set of blocks, but I think usually it begs the question, for the representation learning, do you have to do it in such a heavy kind of auto training, or can you design a supervised task to learn the representations of the net list? I think this is a very good research direction in the sense that, hopefully we can learn a representation from a kind of relevant task, which is not just the placement. But for example, like, you can definitely create a supervised task. Like, in a data set, you have a set of placements, and then you learn the representation just to predict the wire length and also congestion or timing or other metrics, right? So this task can totally be supervised. It doesn't have to be learned through the RO. But I think for the RO, definitely because you're learning on the same task, so likely the representation is a better fit to the specific task, which is the placement. But I do think that learning a generic representation through some other offline tasks is a good idea. Next question from Shafin. Could you describe the purpose of the mask applied to the end of the network?
You can ignore that question now.
Thank you. Next question from Chavez. Would you like to comment on the performance of the placement if other policy training algorithms are used, like DDPG? So to be honest, I think we didn't try all of these different policy algorithms. So at the early days, we do try the value-based RL model like DQM, and we found out that the policy-based RL is working better than that. And for other policy gradient-based algorithm, I think so. This is my take. I don't think that these different policy gradient algorithms could make a huge difference. And I think that because at the end of the day, it's just about searching along the gradient direction, right? It's more important about because this is a non-convex optimization problem, and what's more important is about how you do enough exploration and how you can scale the data collection. So I don't think that a specific algorithm is going to fully solve the non-convex problem. And yeah, we haven't extensively tried other algorithms, but this could be an interesting area. Next question from Irfine. How much the characteristics of layout, like placement density, can impact ML placement performance? For example, we observed in ISPD 2018 and 19 benchmarks with more than 90% of the placement density. I'll be grateful if I can have your insight about the effects of placement density. That's a good question. So the short answer is that because we use in production, so we use a very, very conservative density because we don't, because we can't guarantee what's these EDA tools is going to do, right? When they do the standard cell placement. So we use a very kind of low density target. I believe it's near 60%, which may be overly conservative. But yes, I think if you try using the higher density constraint, then the dream place will kind of place the standard cells in a very different way, and likely drive the RL search directions to very different trajectories. But I think, again, this is probably some kind of hyperparameter tuning thing. And I think a good way to solve this problem is to do some correlation study. So basically, you can generate different placements and with a different density targets, and then you evaluate with the EDA tools. And then you try to find out which one works best, or you can use, just manual or some data-driven approach to find out a correlation between, these, parameters to what the EDA tools report.
So Joe, yeah, sorry to interrupt. I think definitely there are more questions, right? But before we losing many audience, right? I know it's pretty late. I even saw some Japanese audience. It's 2 a.m. there, right? So I just want to thank you again, and also thank all the speakers, Mark and Ismail. Looks like they are still in. But anyway, so just want to remind everyone, right? So we do have another session tomorrow morning, same time, right? 9 to 12 Central Time. You can calculate your time zone by Professor Sachin Sapnecker from University of Minnesota on analog layout using machine learning, and also Professor Song-Kyu Lin from Georgia Tech, and he's also currently with DARPA as a program manager. He will talk about machine learning for 3D IC. And then Shobha Vasudevan, who is also Google research and talking about the verification using machine learning, right? So just want to kind of remind, we have that tomorrow. So with that, you can continue with some, let's thank all the speakers again, right? And also Joe can
Let's
continue.
go back to Joe.
Yeah, so
yes.
All right,
yeah,
thank you very much.
Thanks.
And you can stay as late as,
yeah.
right? As,
yeah,
thanks.
I think the next question is from Jiang Wang. Validation.
Please, we can skip that. It was just a data. But
okay,
please share your screen again, Joe. That was working well. If you can.
Okay. Can you see the? Okay, cool. So yeah, the next question is that it seems that the macros of the case area block have the same or similar sizes. I'll be grateful if I can have insight about the effects of different macro sizes on the quality of the solution. So yes, so this is also a very good question. So for the blocks with a very different macro sizes, this means that it's more challenging compared to placing the macros of the same size. For blocks with the same size, this is effectively a permutation game, right? So basically, because it can exactly fit one macro into, for example, one grid cell. So essentially, the RL agent just need to find a good permutation. But for macros with different sizes, you can imagine that defining the right grid size is an art. So you don't want to define the grid size that's too coarse-grained, so you cannot pack the small macros very well. At the same time, you also don't want to define very fine-grained grid size, and that results in a state explosion for the RL. So this is actually one of the key challenge which makes these kind of crowded blocks difficult, because usually for these kind of crowded blocks, they have very different macro sizes. So we have been working on that direction. So I think a short answer to that is, first of all, we need to define, carefully define the grid size to make sure that we can do the macro packing. And second, we're doing some, research to make sure that the RL didn't get lost when it comes to a very large action space. So yeah, we have some unpublished research that trying to tackle the problem in terms of, having, making sure that the RL agent doesn't kind of, search from scratch, but it needs to bootstrap with some prior knowledge. Okay, going to the next from Gu Hao. First, the article only considers macros that are not overlapping, but the standard cell of clustering are overlapping. How to consider placement of standard cells in the future? So first question is around what if the standard cell clusters are overlapping, right? So eventually, I give all the credits to the DreamPlace because DreamPlace takes care of like the kind of overlapping and making sure that it still meets the density constraint, right? And of course, you can set the density target differently to fit the specific design flow. But basically, RO doesn't directly take care of that. It's taken care of by the analytic placers. And the second question is, how does this method compare with traditional methods such as DreamPlace, training time, and final result? So DreamPlace also has a mixed size placer mode. So we often also compare it to the DreamPlace mixed size placement. And I think one of the kind of challenge in the DreamPlace is, because in the mixed size placement, results in, there might be some overlaps. So for some of the blocks, it's very easy to, de-overlap and legalize the macros. And for some of these, it's pretty challenging. And in particular for blocks with, a large number of macros, sometimes it's non-trivial. Like even if you try doing manually, we've tried that, it's very hard. And so in that case, I think, first of all, it's not a kind of apples to apples comparison because if there's overlap, it's non-usable. But I think one of the direction is how can we kind of design some RL agent to learn how to legalize, the kind of this kind of mixed size placers. I think that could be an interesting, research direction. And next question from Ismail. Why is gradient norm large close to the solution? Yeah, that's an interesting question. So I expect the gradient should be close to 0, right? When it is converging. I just run this experiment, put out that I haven't really looked into that, and that's also a question on my mind. But usually I expect that when it's close to convergence, the gradient should be close to 0. Yeah, it might be at some, I don't know, to be honest. I think I probably need to check other blocks to see, what's the scale of the gradient norm that other blocks has. But this also doesn't sound like intuitive to me, and maybe there's a bug in the reporting.
Oh, thank you, Joe. I mean, it could be that, or if it's constrained, then maybe you have some active gradient, active constraints, and that's making that subset of the partials large. It could be that, but I don't know what's underlying the optimization algorithm. What's the underlying optimization algorithm?
Yeah,
if
there
it
could
was,
be some things.
Yeah.
For example, like because we always do the masking, right? After the policy prediction, so then this masking may have some compounding factor, like affects how the gradient is going.
Yeah. I mean, yeah. If it's unconstrained, like you said, it should be 0. But if it's constrained, then that's yeah, as you know, that's expected. I'm just curious, like you. It'd be good to find out. Yeah.
Yeah, that's a good explanation. I think constraint is that. Yeah. Next question from Arjun. Timing also being considered for the next iteration of the tool. How does timing impact performance and results? So I think we all know that predicting timing is very difficult, right, compared to wire length. So at this stage, I can't say that like we completely solved the kind of the timing problem, but I think we have we're trying a lot of these using either kind of like static timing engine to put it in the RO in the circuit environment to estimate the timing, or using some data-driven approach to estimate timing. Yeah, it's work in progress. Next question from Gasvani. Is there any discrimination in the whole number of occurred DRC errors into interblocks and intrablocks errors in any sense? For example, hierarchical description of blocks as macro. And fixing the ML approach implied that DRC errors is not harder due to tighter restriction in space. I'm not sure I fully understand the question, but I'm trying to guess, like you're saying, how do we make sure that the, this kind of, congestion estimation is accurate and these kind of DRC errors doesn't affect the interblocks, right? Yeah, I think, first of all, estimating a good congestion is also, a hard problem, like in a circuit environment, because all we are doing is doing the global routing, right? There's no way that you can achieve the same amount of accuracy for the detailed routing. So I think something we're trying is like, we through tuning some of the parameters in the routing environment, we're trying to get a good correlation with what the EDA tools report, because they can always report the, the congestion heat map and report congestion metrics, right? So something we're doing is definitely, first of all, we have to tune these parameters in a circuit environment to make sure that the routing achieves good correlation. And this work has to be done for different kind of, I think for different kinds of chips and for different technologies for sure. So I think this is one way to mitigate the problem. And as for interblocks, I think that probably has something to do with the more kind of top level floor planning thing. It probably requires some of the optimization there to make sure that these kind of DRC errors does not go into the interblocks.
Yeah, maybe I can add a little bit comment, right? I think DRC typically are handled during the detail placement, or I think here mostly for macro, right? Mostly still global placement. Yeah, but with some kind of prediction of downstream DRC violation, right? That could be interesting too, right? Well, I think you have answered all the questions, Joe. Thank you so much, and thanks for all the audience who are still sticking around, right? So I think we had a great first day of the seasonal school. Thank you all the speakers again. So Mark, Ismail, and Joe, and everyone. See you tomorrow, right? Same time. So, okay. Thanks. Bye.
Thanks, David. Stopping recording now.
Yeah, thanks, Andrew.